Well, hello there, everybody. Welcome to another SkyTour live stream. It is the 25th of November, 2022. I'm Marc Dantonio, your host of SkyTour live stream, here as always with Daryl Mason. And I want to just say hello. Hi, Daryl. How's it going?
Hello, Mark. I'm well, thanks. You? Hello, everybody.
Doing fine, thank you. Doing fine. I thought we'd open tonight with a very interesting object right here. It looks like a bunch of stars, doesn't it? But in fact, we're looking at this guy right here. You see that one guy right there? Know what that is? That's the second largest asteroid in our solar system. That's Vesta. And it just so happens I actually have a model that I printed, a 3D printed model of Vesta. And here it is. Vesta is sort of oblate. It's not really a spherical asteroid, as you can see. It has a bunch of craters on it. And around its equatorial region, there's a series of really deep troughs that are, well, bigger than the Grand Canyon. So there's an awful lot of detail. And this 3D model renders it very nicely. And if you go look up Vesta, you can probably find this 3D model out there, I'm sure.
You're not kidding me. That's an avocado.
It's not. Yeah, it does look like an old raunchy avocado. It's even the right color. But, yep, it's a solid object. It's a solid 3D print. I printed it out of ABS plastic on one of our 3D printers here. And, Vesta's been pummeled by meteors. In fact, interestingly, Vesta has a surface color that's really interesting because it's been hit by about 300 dark asteroids that are really have very, very dark soils. And so it has it's the asteroid in our solar system that has the biggest variety of albedos, that is brightness changes across it because of this. So Vesta is interesting. And it's also what we call differentiated. It has an outer crust, it has a mantle and a core that are three separate objects rather than being a solid rock. So I think that's pretty interesting how that asteroid has evolved over time. And there it is, right there. Okay, right there in the view. Center of the view. It's the white object. This is a star up here, and then this is Vesta. And we can zoom in on it. You can see it closer, but you're never going to see it as that oblate rock that I have here, because it is pretty far away. I went through a focusing run, by the way, so it's going to not change focus. Actually, the focus is good. So, but there it is. That's Vesta.
May I ask a question or a favor?
Yeah.
I know Vesta was at opposition a while back, but at which time it was closest and you might be most likely to see it. But would you mind trying a few short exposures and see if it shifts over time?
Yes, that's actually not a bad idea at all. I mean, it's not in opposition anymore, but that doesn't matter. We probably can catch something. Right? So let's do this. Let's get rid of the stack. All right, and let's go down to... Let's do our 1 second exposure here and go into our night vision mode. You can see it there. Now, the nice thing is Vesta right now is against this background of other stars that are pretty obvious. Let's just do a 15-second shot and see what that gets us. All right, this will be a 15-second shot of Vesta, and we're going to go back into the stack and we'll clear it. Alright, and see what the 15 seconds shows us.
A little bitty green thing there to the lower right of Vesta.
Yeah, we're going to find out what that is too. Okay, so let's... Alright, so we have some noise, and when we see the second stack come in, you're gonna see a lot of this noise go away. That's what stacking does for us. It eliminates the noise while letting the data come through. Look at that. Suddenly it's a lot clearer, and it'll just keep getting clearer. So we'll just let this go till about 5 images, and then we'll move on. And when we come back, we'll see these 2 stars or these 3 stars in relation to Vesta and see if there's been movement. All right. So that's pretty cool. So is that what you wanted to do?
See it move?
Yes.
Or see if it does move for us. Sure.
Well, we probably have to come back like 45 minutes from now and check it out.
If you like.
But that's what I'm getting at, is we probably have to do it at 45 minutes. I want to say hello to everybody that's here, first of all. I want to say hello to the number 1 person that got here first. That was Multi Haystack. How you doing? Nice to see you. Yasser's with us. And Robin Curtis is with us, otherwise known as Database Girl. And Dan Norton. How you doing, man? Bonnie, Anahata77 is dropping by. Renee Cruz is here. And, hey. And then we have Cosmic Ray. What's up, man? We have Paula Trades. Nice to see you again. And we have Sam S. And, who else? Bullwinkle. Hey, man. How's it going? And look at that. Keith is here. P&K. What's up, brother? Cindy Murphy and Papa Tom. Good to see you as well. So, I figured, okay, we've done 7 of these. So now we'll just pause it right now. And we will name this Vesta 1. And then we'll come back and we'll save it now. All right, and save it exactly as seen. And this will be our base point. So when we come back and look at this later, we'll see if it's moved against these stars. See the stars here that are sort of framing it? We'll see if it's over here a little bit. We'll find out. All right. So there we go. Michael Galea is with us. Izabela's here. Hi. All right. And let's see. All right, we're going to bring down our magnification. And we'll get the entire frame in here.
Will it be where you can get at it again later, so we can maybe do a toggle or something?
Maybe. I mean, certainly. I mean, the image is not will be up on the database if it's not already there. It's going to be there in a moment.
Very good.
And we'll be able to do it. Asher, how are you? Asher Rail is here. Thanks, Asher. He says, great to be here with you tonight. That's very nice. All right, so we're just checking out some objects tonight. And I've been doing some really interesting stuff. I got a call, not a call, but a message today from an astrophysicist. And they want to use one of the astrophotos we did of the Dark Nebula region for one of their little projects. And I, of course, said sure. And
Cool.
They work with infrared systems, including James Webb stuff. So it might be down the line. Who knows what might happen? I'm looking forward to all the possibilities. She's on the ball with everything she does. She's at
You'll
Caltech.
be published.
Well, I don't know. I mean, I've been published before, but this is different. I haven't done that. Published in journals at all. This would not be a journal publication, I don't believe. Hey, Alice Pooper.
Closest I ever came back in the days of film, I sold a couple images. One of the lunar eclipse back in November of '93, I think.
Oh, yeah.
And, then Comet Hyakutake and Hale-Bopp.
Yeah.
I sold a bunch of the eclipse.
Oh, that's beautiful.
And Hale-Bopp.
Mm-hmm. All right, we're going to check out the Helix, which is right near Vesta. Okay.
As Cosmic Ray pointed out. But yeah, it's still in, is Vesta in Aquarius?
I believe it's just in Aquarius, yeah. Let me look back here. Yeah, there's Vesta. That's in Aquarius.
Yep. And then...
Okay, so let's center this up.
the Helix is under Aquarius or in Aquarius, I forget.
Mm-hmm. Well, it's in it, but okay. So we'll let this come in. Tara and Marie, how are you? Nice to see you. Nice. If any of you want a good read, you might want to go to Amazon and pick up the book, The Populated Universe. It's a book I wrote, which has been out for a year and a half now. Can't remember. It's a pretty good sized book, and has a lot of color illustrations I did myself. It's amazing what you can do with a crayon. Just kidding. And it's a book that discusses what I feel is the truth about the universe, and that is that life is the rule, not the exception in the universe. Whether it's life that we would recognize remains to be seen, because the way life turned out on our planet was the result of a number of extinction events that happened here. So, in fact, getting hit by things like this, by these asteroids, right? I mean, getting hit by an asteroid is definitely a big problem. Oh, look, we have a satellite coming through. It's a 1 second exposure, so this is taking 1 second to come through. That's all right. Let's do 40 seconds on this, and oh, here comes a Starlink satellite now. That's the size of a Starlink satellite path. So I suppose that's what it is. Okay, we're going to capture this now, 45 seconds. We'll go into our live stack and clear Vesta. Yep, it's hard to go through anything and not see satellite paths. You know, that's unfortunate. Okay. Hello, Daisy and Zoe. It's nice to see you guys here. Zadarak is here with us too. Nice to see you. All right. And let's do this. Yeah, look at that. Zing, zing.
Yeah.
It's all right.
Aquarius is slipping away.
Yes, it is.
I know you can only see the very last bit of Sagittarius low in the southwest after sunset now.
Right.
Nunki, the bright star that handled the teapot.
Mm-hmm.
And he's gone, and then it's Capricorn, and then Aquarius here, and, constellations, even of fall, are going away in the south now.
Yeah. So this is... Okay, go ahead.
No, when you see Saturn now, he's still up, but he goes away by 10 o'clock. And Fomalhaut not long after, and down in Pisces Austrinus, and Jupiter's in western Pisces, and he's going away pretty quick too.
Yeah.
Sorry.
No, that's all right. Okay, this is the Helix Nebula. And the Helix Nebula is the remains of a dead star. You can see if we zoom in on this, okay, and when you stack, the noise that you see, this modeling here, goes away little by little. We can also remove it by doing stuff like this and by pulling these levels in a little bit. And you can see there's stuff out here. This beautiful ring, which has these radial streaks that you can just barely see in here, are all coming from that one star in the middle. And we call it a star, but it's actually the remains of a star. It's a white dwarf. The white dwarf is a very strange end state for a star, about the size of the sun. And that's when a star swells up into a red giant but doesn't go supernova, it eventually shrinks back down and collapses to a white dwarf. And that's what we're seeing here. The white dwarfs are very hot which is why that star is actually blue compared to these stars here. You notice blue is hotter than white in the universe. Blue hot is the hottest there is. And this particular star is actually extremely hot, and it is ionizing all the gas that used to be in its envelope. The thing that made up the star, all right, was sloughed off as the star was pulsating as it got older, and it went into red giant, shrunk and expanded again, and it pushed off these outer layers in these concentric rings, and thus it ended up causing what you see here, this nebula. And then the white dwarf, being so hot, ionizes the gas. Oxygen is the bluish green, and hydrogen is reddish. And again, considering the abundances of hydrogen and oxygen in the universe, hydrogen is the first most abundant gas in the universe. Oxygen is the third most abundant gas in the universe. Okay, so in between them is helium. So clearly there is a expectation that you'd see a lot of blue-green nebulae and a lot of red nebulae, because when they ionize, when those two elements ionize, these are the colors you get. It's a glow. That's a sort of a simplified approach. In reality, it's got to do with electrons moving to different states in the atom as they return into the atom from ionization. But it's really pretty nonetheless, and that's why most planetary nebula we see are this bluish green, because there's usually a lot of oxygen in those envelopes of those stars. And the oxygen doesn't help the stars burn anything, because the oxygen is just elemental. Okay, it's not O2 like in our atmosphere. That's a molecule. These are atomic nuclei that we're looking at, just an oxygen nucleus. All right. And burning is a chemical process. Fusion is not. Fusion is a nuclear process. It's a nuclear process known as nucleosynthesis. That's where that comes from. So that's what makes the energy in a star. And the white dwarf will cool over time and eventually become a black dwarf. Now, I don't think the universe is old enough for us to see any black dwarfs yet, because it takes billions of years for these stars to cool.
How would we see them?
Well, we would see them by whatever remnant they have left behind in terms of gravitational anomaly with planets circling, or the fact that there might be some type of radiation being given off, like heat. Okay, you might see infrared. You might see infrared sources that could be a black dwarf that's no longer luminous.
Yeah.
But that's about it.
Might be a long time from now, too.
Oh, yeah, yeah.
I see a big green eye.
Yeah, it looks like the Eye of Sauron, right?
Even has an eyebrow.
Right here?
Oh, to the upper left.
Right there, that eyebrow? Or this?
To that right there.
Okay.
You could call that other one closer in eyelashes.
I guess that's true.
He looks angry.
Mm-hmm. Maybe.
I'm always amazed by the corkscrew appearance of the thing, why they call it the helix, It looks like it's done several rotations.
Yeah, it has an interesting background. We don't really even know what it's done in the past. It's like looking at a car sitting on the road and trying to reverse engineer where it's been.
Yeah. Well, as you say, it's a 3D universe, and we're just getting a two-dimensional look at it.
That's correct. We are. That is exactly right.
Is it a torus? Is it a cylinder almost face on to us, or?
Yeah.
Looks like a torus to me.
Might be. Mike Hedrick, how are you? Richard Spencer, good to see you. Wow, that's neat stuff, man. I tell you, it's a fun nebula to look at.
Hedrick, I think Mark answered Asher's question. It's not burning per se. The elements were fused in the star, And now, since the star has turned into a white dwarf, just the gas that it has put off is being excited and illuminated by the high energy radiation coming off the star, ultraviolet and such.
Yeah, this gas you see here is,
Ionized.
A light year or more away from the star. It was sloughed off when the star went into red giant phase and just kept going because there's nothing to stop it. And as it expanded into the interstellar medium, it was being excited by the white dwarf's radiation, which is a lot of ultraviolet radiation, which ionized those gases. Many of those gases, some were possibly made in the core of the star, but more than likely what you're looking at are the gases that were actually in the envelope of the star when it was made. And these were just being released back into the interstellar medium. A star like this doesn't go supernova, so you don't get all of the elements in the core blasted out into the universe. You just get the outer envelope, and the core shrinks down and compresses into this white dwarf. Now, interestingly, the white dwarf doesn't have any fusion going on at all. This is just seen by the residual heat that it had as a star. And as you can see, it's very hot because it's ionizing gas. And the surface of the white dwarf is a really strange place. It's made mostly of carbon and oxygen atoms, very, very tightly packed, oxygen nuclei, I should say, tightly packed. Okay, no atoms at all, right? But there's electrons, and the electrons are packed so close together that you can't put any more in there. And as the star tries to contract, it gets smaller. Those electrons, think of it this way, are getting pushed near each other, and they have their own pressure, because obviously, negatives repel and positives repel, and the negative, think of it that way, the electrons are repelling each other, and it gets to a certain point where the electrons are successful in holding that star from collapsing any further, and that's called electron degeneracy pressure, and that's what's holding these white dwarfs together. Really fascinating,
Hi, Marianne.
Marianne's here. Hello. Neutron stars do the same thing, but as you can imagine, it's not electrons or electron degeneracy pressure holding them up, it's neutron degeneracy pressure. The neutrons are pushed together. Again, there's no atoms. They're all nuclei and particles, elementary particles. So that's really what happens when these stars get like this and in this state. And then, of course, above 2 solar masses for a nucleus, you're cutting over into, the neutron star territory, and then above that, 2.4 solar masses in the nucleus or the core, the remaining core of a star. That's black hole territory. So.
Yeah, and there's a slippery slope once stars start dying. A gradation from the regular star, how dense it is, which isn't overall very dense, just a lot of it, and it's big.
Yeah.
And then it turns into a white dwarf, and you've heard before, like a tablespoon of white dwarf is going to weigh a lot. But then if it collapses to a neutron star, that same tablespoon is going to weigh a whole lot more.
Yeah. About 1 billion tons on Earth.
Yeah.
In a tablespoon. Can you imagine that?
Yep.
Very interesting. Okay. Well, we did 17 of these. We'll do the 18th, and then we'll stop it here. You can see that the image is much more cohesive now. There's not a lot of noise in it anymore. Let's do a color correction here. There you go. Now we'll pause it, and we've got Helix Nebula named up here, and so we can save it and save it exactly as we see it. All right. Okay, and now we can get rid of the stack here and go back to our night vision mode here. There we go. All right, and then go to this right here. It's about full size here. All right. Let's check out something else here. We don't need that anymore. Pull that away. While we're on this side of the sky, what else can we look at here? Let's see. What about the Sculptor Galaxy?
Yeah, that's going to be what my suggested.
There it is. I think that's the one, right?
I think you're right. Or the one a little farther to the right.
Yeah. This is the southern pinwheel. That's a little dimmer. And this one I don't think is it. But I do think this was the one that's it, right up here.
Ring of Pearls.
Yeah, that's the one.
Sculptor Galaxy.
Yeah.
We did the southern pinwheel recently, did we?
We did, but it was a little bit dim because I didn't do a very long exposure on it.
Okay.
So, okay, so let's see here. Interesting. This
I don't
one,
remember that.
no, it's a kind of a weird one called Needle's Eye. That's an odd name. Well, it's an essay. Yeah, let's check that out and see what it looks like. It might be
Say how big it is.
21 minutes.
That's not bad.
Let's check it out. And then we'll go down to the Sculptor Galaxy. Okay, watch the telescope. You can see it's moving now over our heads. And it should head right for the Needle's Eye Galaxy. Hello, Judy McClelland and Renee Cruz. Well, there it is. That's not a bad size.
Yeah. In a 1 second exposure, especially.
Yeah. So we'll do a 40-second exposure. And let's move it a little bit to the east here. Okay, that's good. And once we start guiding, we'll lock on. Takes about 14 seconds to acquire a guide star. Hey, thank you. Thank you very much. That's very kind of you.
I wish I could say your name.
And me too.
Thank you anyway.
All right. So now we're guiding. We're stabilized. Let's do 45 seconds. And back out and go to our live stack. Remove the previous stack. That's what it was. That's up in the database right now. So we'll clear this. And now we'll see the Needle's Eye Galaxy.
Wrong hole. Sorry.
Yeah.
I inhaled my tea.
Okay.
Edric has a question.
All right. Edric, what is the second camera above you? The video above the telescope. Oh. What you're seeing is you see the main. Oh, look at that. You see the main telescope body. Okay, color correct first of all. You see the main telescope body. Then you have a second camera on top of the telescope. It's a long telescope on top of the telescope, if that's what you're talking about. And that's actually the guide camera. It's a separate guider altogether. In fact, you're watching the guider right here. These are the guiding parameters. As we're taking exposures, it's actually altering and changing the movement ever so slightly of the telescope to correct for any guiding errors.
Yeah. It's actually the top of the keypad that controls the telescope.
What?
I said your guide information there, that's on the top of your keypad, isn't it?
This right here, yes.
Yes.
Yeah.
It's a computerized keypad that operates a telescope on its own, it would anyway.
Yeah. Okay, so we're going to get more coming in here. Let's play around with this. Okay. That's interesting. This looks like a galaxy. It's not quite edge on. It's sort of like this. Really interesting.
Yeah.
Looks like it has a gap here. It looks like this gap could be something that might have been induced by interaction with another galaxy, perhaps.
Yeah, I think that's the eye of the needle.
I think that's why it's called that. Exactly so, yeah.
Looks like there's a star in the hole there, but that star is surely a foreground object.
Yeah, these are all foreground objects, I'm sure. Because this particular galaxy, according to our planetarium system, is 11 million light years away. And that's pretty distant.
Interesting looking though.
Yeah. Okay, so let's go back and...
See, it's not far from Sculptor Galaxy. I wonder if they might have interacted at one time.
That's a good question. I don't know.
How's that? How's the formation of the eye-looking thing?
I know. It could be.
You can see some detail inside the galaxy that I don't think are foreground. There's one at the very top, right at 12 o'clock.
Mm-hmm.
Kind of a little fuzzy, and then when you get down around and just below the nucleus, there's details to both sides.
Yeah.
I see a little tiny dark vein there, and maybe more nebulous or star cluster objects to either side below center.
Yeah, I'm going to add the enhancement now. Ready? Here we go. Okay, I added some enhancements. Now you can actually see. I mean, I can add a ton of enhancement, which would really not be too smart because it really is a lot. Okay, so I'll give you an idea. Okay, we had a reset just happened out there, so I gotta just come in here really quick and bring this back.
Look, there's several additional small galaxies to the left and the upper left of
Yeah.
There's three of them in a row there at about 10 o'clock.
Yeah, yeah. All right, hold on.
And one on the right over at about 2 o'clock.
Yeah. That's interesting right there. That's a feature in there.
Uh-oh.
Yeah. Hold on a sec. All right, just a minute.
Hello, James Dugan.
Oh. Hey, James Dugan.
Mark forgot his password.
No, I did not. I did not forget my password. Hang on, folks. I'll be right back with you.
I hope everybody's having a good evening. I hope everybody had a good Thanksgiving.
I know. It was a great Thanksgiving here. Very quiet. Hey, Uberku.
Yeah, I cooked Thanksgiving dinner. Turned out great again this year. I had a lot of practice. I've gotten pretty good at it.
Yeah.
Of course, now I get to eat Thanksgiving leftovers for the next week or two.
Yeah. There we go.
But hey.
Oh, look at that. All right, let me add a reset here. So I have to just go bring these things over again. There we go, right there. All right. All right, we'll color correct again here. All right, look at that. That's got some really nice detail. How did we miss this before?
Oh.
How did we miss this before?
That is interesting. Can you zoom in on it?
I suppose I can. Let me do that right now. There we are. There's a little too much. All right.
That's a lot of detail going on in that thing.
Yeah, let me add a bilateral filter. Reduce the bilateral filter substantially.
Mark, say hi to Marianne.
I said hi to Marianne right away when she said she was here.
Oh, okay. Hi, Marianne. She's so nice, you say it twice.
All right. Yeah, well, she is. She's, for those that don't know Marianne, she's actually one of the movers and shakers with SkyTour LiveStream. She's one of the real people behind the scenes. Okay, her and Tara Diulis. Daryl and I, we're just the hosts. I'm just the host of this, and I'm just an astronomer. This is kind of what we look like. We wear flannel and whatever.
I'm wearing my flannel.
Hey, it's winter. It's cold.
Yeah. Got my warm socks on too.
Awesome.
I love that. That's got tons of detail in it.
Yeah, I'm going to shut off the bilateral filter because it's actually taken away from the detail.
Some at the very bottom and one up a little way toward the left side, and light dark clouds higher up, and then there below the nucleus on both the left and the right there's stuff going on.
Yeah.
And above the nucleus, and I see some greenish or grayish nebula kind of stuff up toward the up top right.
Yeah.
One at the very top and one down about a fourth of the way.
Claudio Ramos asking a question, do I have Instagram? Yes, I have an Instagram as Marc Dantonio. I don't know if it's SkyTour LiveStream though. That would actually makes sense. So I don't know why I didn't do it. And up near the clock, he's asking about, Mike Hedrick is asking about this right here.
Might be a satellite galaxy.
What I'm wondering is, did it cause this? That looks like it may be it might be a more distant galaxy. You know what? Let's find out. Let's go look at the tip of the needle galaxy here, needle's eye, and let's go see if this galaxy is in here. There's another galaxy over here, which I don't think is the one. That's that galaxy. It doesn't give its distance. It only gives the redshift, which means it's really far away, much farther away.
Wiki says 11.1 plus 1.2 million light years away.
For what, the needle's eye?
Yeah.
Yeah, that's what we saw. It said it's 11.4 in here, but still. Yeah, we mentioned that before, but I think that what I'm interested in is what Mike Hedrick was talking about. It's actually it's right here.
Yeah, that thing up at the upper right.
Yeah, right there. That's actually... Yeah, look.
Okay, there.
It is another galaxy. It is another galaxy. I think our picture's better.
Does it identify it?
No. It's a field galaxy. They don't even identify it. Wow, look at that. So this is what they call an SAB. Now, the B is capitalized, so it's capital S, capital A, capital B. And that means that it's what they call a barred spiral galaxy. The nucleus is extended. It has a nuclear bar, which is a little longer, and the spiral arms come off of that. So because it's sort of on edge, we can't really see it face on. We see it sort of on edge, and that shows us a little bit more about what it looks like. Okay, you know, if we can see it face on, that is. But unfortunately, we don't see that here. But we do see some of the details, like this area here. In this, we actually see in here. We see those same details right here.
It is a member of the Sculptor group.
Yeah.
Sculptor Galaxy 253 is the center, of course.
Mm-hmm.
There are a group of other galaxies around it that are all bound to 253 also.
Okay.
Group.
Well, we're going to go to 17 exposures. As you can see, we've done 16. We'll go to 17, and then we will save this as we'll call it the eye of the needle. Or is it needle eye? Needle's eye. Let me make sure. It's NGC 247, needle's eye. So we'll call it that.
A lot of H2 regions in it also.
Yeah.
We're seeing them only weekly. A lot of red in them in images.
Yeah. Okay, we got 17. We're going to pause. And we'll save Needle's Eye Galaxy. Think about this, guys. You look at this galaxy, you're very likely looking at other life that might be looking back at you. That's really, really cool. Really cool. All right. I see something else too, right here. So there's something there as well.
Yeah, I mentioned that earlier. There's actually one there and 3 or 4 in a row above it. 3 in a row, I believe.
Yeah.
There's a couple of small spiral galaxies to the upper left.
Mm-hmm. There's some right there. 1, 2, 3 right there. 1, 2, 3.
4.
Is there a fourth one there? 1, 2, 3, 4. Oh yeah. How about that? Very cool. Yeah, so if we zoom out of this now.
That bright spot up just past 12 o'clock, that's an H2 region.
Right here,
Maybe
you mean?
maybe if you process that, you can tease some pink out of it.
Yeah.
There's a lot of H2.
I see pink right here. There's a pretty large one right there in the needle's eye. Isaac J. Newton, what's up? Hey, Greggy Gilgan, how's it going down under? How are things out there? I'm going to have to get something to drink here in a sec. Okay, let's clear this.
Nice little galaxy.
Yeah, I'm going to just save it in case I didn't before. I don't remember. I think I did, but... Okay. Yeah, that's a lie. It did do it. Okay, now we'll clear it when we come in again. Put on 1 second. And go to our night vision system here. Okay, night vision in place, activated. All right, so now we're gonna pull out too far. All right, there we go. Come back here. Okay, now we're gonna go to the Sculptor Galaxy, which is right below it. Yeah. Just below it. And there it is. The Sculptor Galaxy is another gem.
Well,
We're going to head there now. So if you watch here, telescope's not going to move very much right there. You're going to see it move a little bit, and then we're going to see that. This is hiding in the dark, the Sculptor Galaxy.
sometimes known as the Silver Dollar Galaxy.
Silver Dollar Galaxy. Yep. The Silver Dollar Galaxy's got some really interesting features in it. If you thought the other galaxy was cool, well, just wait till you see this. Yeah, I'm going the wrong way. Oops. I meant to go to my other east.
Other east.
Yeah. There we go. All right. All right, and this is a all right. So this guy that we're looking at is that guy, Sculptor Galaxy, and what we're going to do now is we're stabilized, we're guiding. You can see our guiding over here. The numbers look good. All right, so now we're going to come up here and get out of this. Those things are going to go away. Hold on a second. I don't know why I just did that. Oh, I see why. Duh. We're going to shrink that down a little bit. Okay. Alright, and then we're going to pull this back up. Just getting everything placed in the screen properly, that's all. Nothing to see here. Move along. And there we go.
Rawhide.
Yep, there we are. Okay. Now we're going to do our exposure. We're going to come in here and say 45 seconds on this. And off it runs, because we've been tracking very nicely. All right, we're gonna drop into the black and go in here. So this is the galaxy we just took. That's the Needle's Eye Galaxy, and it's called that obviously because of this gap up here. It looks like a needle with an eye of a needle. And our telescope.
Wiki said something interesting about that needle's eye.
Who did what?
Wiki said something interesting about the eye of the needle there.
Okay.
All the blue stars are gone inside that eye, but there are still a lot of red stars in there.
Yeah. That's weird. I'm not sure what that is from. Here's the Sculptor Galaxy. I'm going to pull back some of the data. We actually kind of did too much of an exposure on it, so we're going to actually pull some back. There we go. And now you can actually zoom in and see this beautiful core of this galaxy as it develops. You may notice that our guiding and our stars are nice and round, and we're doing long time exposures at a magnified view. I spent a significant amount of time over the last couple of days working in here, from long distance, of course, to optimize how the guider works. And we can now do 1 or more minute long exposures with no problem, but I'm not going to subject you to them, because if you think of a stack of 15 stacked images, that's 15 minutes at a minute. And with all the additional stuff going on, it could easily add up to 20 minutes of overall time. So it has to be one heck of an object to do that with. Alright, so let's do a little color correction. There we go. Look at the detail in here. I'm going to do this. To show the detail even better, I'm actually going to turn off this enhancement. Watch the center of this galaxy. Watch how it changes when I turn this off. You're going to suddenly see it so much better. Look at that. See all the detail in there now? That's beautiful. And this, we'll turn the enhancement on later, but I just wanted to show you this. Okay, this, we're right here. This is the native scale of our sensor. We are at 100% on the sensor. This is what it wants to be. And we can view even higher typically, but I'm going to back us out to about 50% or so. Well, no, let's go into about 65% or so. There we go. That's pretty. Yeah. And that's the Sculptor Galaxy. And we're going to stack a few of those. We've got 4 stacked so far. Let's put that down there. Let's get rid of the telescope for a minute. There we are. Now we'll bring this down. There we go. Look at that.
That's nice.
Oh, yeah. It'd be great if my face wasn't in it. It's showing beautiful detail. Yes, indeed. Claudio says great detail. Absolutely.
A lot going on in there.
Oh, yeah.
Somebody said earlier it's a starburst galaxy.
Yeah, that was Ray.
Yeah.
Cosmic Ray. Yeah, it's just it's a lovely galaxy. When I look at galaxies like this, again, coming from the perspective as an astronomer whose tact is to look for extraterrestrial life, I look at this and think of this as a fertile home for life, a fertile location from which life could spring. I think galaxies are basically big incubators, because the way they build hot blue young stars first, those hot blue stars go supernova, release all kinds of core fused elements into the interstellar medium. Those become the raw materials from which new stars can be made and planets can be made around those stars. And it's amazing how everything in the universe sort of has a place. Very interesting. Thanks a lot. What's up? Okay, thanks a lot says, kind of a cool statement. Life will have to find us because we don't have the tech and probably won't for thousands of years to find them first. I will explain to you why that may not be true. I've actually been lecturing all over the country about this. I did this talk in Roswell. I did it in Denver. I've done it on several podcasts. I've done it on television shows. I think the truth is, okay, seriously now, the physics is there to understand how alien ships, if you will, could be here. And it goes back to the fundamental 4 forces, right? We have the strong force, the weak force, the electromagnetic force, and gravity, of course. And, the strong force and the weak force, well, those are the reasons you're here, okay? Decay allows atoms to go from one to the other. Electrons, added to an atom, form other atoms. As a proton count increases, you get the subsequent electron count. As neutrons get turned into protons through decay, then this process creates higher elements in the periodic table because we go by number of protons, right? 1 is hydrogen, 2 protons is helium, etc. So, so when we look at how alien life might get here, you actually have to look at really the way gravity works. And isn't that, lo and behold, the big problem? We don't know how gravity works. We have ideas, and people say, let's talk about quantum gravity. Well, what is quantum gravity versus, F equals gmm over r squared, which is the universal gravitational law? Okay, well, it really comes down to this. If a ship is going to utilize a process to get here, it probably has to create very, very high gravitational fields. And when we think about very, very big gravitational field generating objects in the universe, what do we think of? Black holes. So we think, we got to harness a black hole in our ship and carry it around with us. In fact, we don't. In fact, a fusion reactor, once we can get a fusion reactor, is all we're going to need to generate the particles needed to go from this galaxy to that one. And you're like, well, what are you talking about? That's science fiction crap. You're just talking out of your butt. No, actually, it's not. It's actually part of Randall-Sundrum 1 string theory variant. And what that means is we are on an XYZ moving through time. That's our membrane, as in string theory terminology. Sorry about this in a way. Okay. And that membrane is our universe. Okay. It's our home membrane. Well, next to us and those are 4 dimensions. Next to us is a 5th dimension called the bulk, B-U-L-K, in this theory. And it's highly warped. If you could go into the bulk, you'd find that all distances are shortened around you. Everything is shortened, very, very shortened. Well, how do you get to the bulk? Well, we can't get to the bulk directly, but if we generate particles that live in the bulk, then our ship would be dragged into the bulk, at least partially, until we let the particles bleed away, and then we'd come back into the 4 dimensions that we know. And that traversal into that 5th dimension, again, shortens all the distances. So the distance from here to, say, Alpha Centauri, instead of being a 10,000 mile trip, or 10,000 year trip in our spacecraft, would be a 20-minute drive, effectively. And that's only a short little, putting your toe into the bulk. That's not going further into the bulk. Okay, that 5th dimension. And how do you go into that dimension? How do you generate particles that'll take you into that bulk? Well, you can thank 2 folks, Kaluza and Klein, for doing research on the Kaluza-Klein particle, because the Kaluza-Klein particle can also be a graviton. Now we don't know whether gravitational particles exist. That's a graviton, like a photon, graviton. We know about photons. We know about fundamental particles. And we also know that the fundamental particles can be described with wave equations, right? So there's wave nature, particle nature. Well, we know gravity is a wave nature because we see gravity waves. Daryl talked about it the other night. The LIGO detectors. They detected gravitational waves from colliding black holes and colliding neutron stars. But we haven't seen the elusive gravitational particle. But if they're there, they may take the form of the Kaluza-Klein graviton. 10 to the 16th times more powerful than the gravitons holding you to the seat you're sitting in right now. And if you use a fusion reactor to create those and surround your spacecraft with them, something amazing happens. Those particles exist in this 5th dimension. So if you generate them in the 4th dimension, they're automatically going to pull you into that 5th dimension. And when you get into that 5th dimension, you can then punch out of the 4 dimensions and punch into the 4 dimensions anywhere you want. It'd be like a punch out, punch in process. So, that said, to go to this galaxy right here, maybe you have to punch in and punch out 400 times to get there, maybe 1,000 times for all I know. But the ship's going to do it. You just sit back and wait the 10, 20 hours or 14 days, whatever it's going to take to get there. But the fact is, this process, using Kaluza-Klein gravitons to do this, might actually be how they're doing it. And it's not just Marc Dantonio talking about this, okay? Robert Schroeder, a physicist and aeronautical engineer, wrote a book about it. I've talked to other people that think this is very plausible, but we don't have proof because we can't yet prove string theory. It seems very plausible. Now, what is string theory anyway? And that'll be the last thing I say before we move on. But if you think about, we talked about particle nature and wave nature, right? Well, if you have a particle, a proton, it's going back and forth like this, okay? It has an endpoint over here. You see the particle there, then you see the particle there. Everything's moving. Everything's vibrating, right? Well, if you don't look at the particles at each end, but just look at the path they went through in the middle, That's the vibrational path. That vibrating path is what we're going to call the string. Okay? So we're just looking at the energies. This vibrating path. Very, very small strings. And if we look at those are the things that we're talking about here. And those strings in Randall-Sundrum 1 string theory are essential to understand how these Kaluza-Klein particles can pull that ship into the bulk, as it's called. So, in a nutshell, I just gave you a 2-hour lecture in 7 minutes, about how alien spacecraft may actually really use physics that we can almost see but can't quite do to get here from there. So there. Daryl, of course, is asleep. He's like, here he goes again, But hey, we're getting good shots here. This is 17 stack. We're going to go to 18. Okay, this will be our 18th shot, Daryl.
Okay.
Let's get back to telescope view here. All right. Okay. Let's go here. We'll pause this. Change this to the Sculptor Galaxy. Any requests, Daryl?
Excuse me?
Any requests? Would you like to see?
Not offhand. Let me think about it a little while.
All right. Okay, Sculptor Galaxy, saving the raw file. Save exactly as seen. Look at the detail. That came out really nice. Should we zoom in on that?
Sure. Can you try to brighten that just a little bit?
Yeah.
I know you manipulated something to give it a little more detail, which is fine, but
Yeah, I can.
seemed quite bright but legible early on.
You mean like this? You mean?
Yeah, I guess.
Let me zoom out a little bit.
Nice picture.
It seems like there's a dark tail over here of something. I wonder if it's well, it's a starburst galaxy, so I'm wondering if we're seeing stars outside the confines of the galaxy in some abundance.
I wish you hadn't said that. Now I see dark streaks.
Well, it's true, right?
I saw one to the lower right too.
Yeah, there
But
was.
it goes away if I keep looking at it.
Yeah, it might be an artifact, actually.
Persistence of vision or something.
Yeah. All right, let's do this, and let's actually...
That's a heck of a galaxy.
It's beautiful, yeah. Do a little color correction, and as you can see, the guiding is gorgeous. We're doing just great with the guiding. I love this. Okay, so that's cool. So now that we've saved this, I'm going to do it again anyway. Save exactly as seen. Yeah, it always says that, but then it does it. Then we'll clear it. Alright, and let's now go to our night vision system. Why does it do that? It went the wrong one. Okay.
Try that other galaxy you gave short shrift to last time.
Which one?
We talked about it earlier. You said, Southern Pinwheel?
Oh, yeah, Southern Pinwheel. Yeah, we could try that
We
again.
looked at it. We didn't stay there long.
No, it's right here. Might as well. So that's a third galaxy. So far, we've seen about 7 or 8. The reason I gave it short shrift was because it was down so low. Oh, that's the giant squid. That's not the one. Where was that Southern Pinwheel? Is that even below that one? Oh yeah, there it is. All right, we're gonna try it, and we might end up having the building in the way. That was the problem, I think.
it's too far south, it's too far south.
Yeah. There it is. It's very faint. But let's give it a shot. Doesn't look like it's too far south. I don't see any interruption by the building. And just so you guys know, which first of all, let me get rid of this right here. We don't want that. If you can see down here, it says temperature minus 19.8 Celsius. It's very small, if you can see it at all. And that's actually the temperature of the sensor. So it's pretty cold. We run this temperature very cold to eliminate noise on the sensor. All right. Okay, now let's give this a 50-second. And we're at 450 gain, by the way, just so you know. I don't know if you noticed it there. We've been running at 50 higher than our highest.
Ooh.
Hey, yeah. Okay, here we go. So 50 seconds, and you see the progress bar down here, lower right over there. The yellow bar moving slowly across, and now we're going to come back in here and go into our stack. And this is our Sculptor Galaxy from before. It really looks pretty. I gotta just see it one more time. And that's going up to the site. Okay.
Thank you, Izabela.
And we'll clear it now. Ah, yes, Izabela put the folder up there for you all to see. Thank you. And if you don't know where to go, go here. SkyTourLive.com. You can also go to SkyTourLive.org. And this will show you all of the things that you want to see. The blog has not been updated. I was going to put a blog post up, but I went so fast getting this going that I didn't put the blog post up saying join us tonight for a stream. And the 20 seconds is up there, not today's. Okay, let's and I will take care of that. So now let's do this. We're zoomed in pretty good here. Wow. We should let that develop for a while, Daryl, and see what we get. What do you think?
Sure. It does rather remind one of the Pinwheel.
It does. A little bit.
Maybe after this, if you want to take one last look at Vesta for tonight, we can see if it's moved.
Yeah, Vesta would be good to see after this. That's kind of why I'm doing the galaxies, right? Kind of stay on this side of the sky. Go check out Vesta.
Well, as I said the other night, this time of year, there aren't a ton of galaxies, but there's a lot of really nice galaxies.
Yeah, that's right. And we tend to find them.
Yep.
And I like that we could. All right, let's...
Izabela, it's called the Southern Pinwheel. See if I can get some more information on it.
All right.
Are you drumming your fingers?
I was going with the song that you can't hear. Okay.
Oh heck, this is Messier 83, no wonder. Can you pull up the data block on stellarium?
Yeah, maybe. Let me see.
Make sure it's
Yep.
talking about the same object.
First, I want to say hello to C&D Boy. How's it going up there in Canada? And Luis Rodriguez, how are you? Welcome to the SkyTour live stream. He asks, what would be the most interesting galaxy to search for life? You know what? I do have an answer for that. And it may sound rather ordinary, but the fact is, I think that the Andromeda Galaxy, it's close, and we could actually look for exoplanets in the Andromeda Galaxy. So the Andromeda Galaxy might be a good one. And C&D Boy going, I'm glad. Thank you for the response. So you looking for the data block on the southern pinwheel?
Not now.
Oh, well, I had it. Okay.
Yeah, we may be talking two different objects here.
Okay. And liminal Andromeda. Yes, because it's close. Exactly right. If it's close, it's an advantage to us to find life close by. That's why we look for it in our solar system, because we have the best chance of studying it when it's here. And hello to Desert Dweller.
Okay, this is not M83. It is NGC 300.
Yep.
As Stellarium said, and it is a very nice spiral galaxy.
Yeah, it's Caldwell 70. Okay.
And it even has a lot of big H2 regions in it, like M33 does.
All right, well, we're going to see if we can tease some of that out. Oh, yeah, look. We're getting some H2 regions here and here. There's some in here you can see those pinkish regions right there. So we're getting some there.
Big blob, the one up at the top right.
That's that one. That looks like an OB association because it looks sort of blue. But is it actually an H2 region? I see one here that looks like an H2 region.
It's pink in the
All right.
image I see.
Well, let's see what the color wants to be. Okay. By the way, these diagonal streaks, I have figured out how to get rid of them, and it requires a visit to the building. I have to take apart the camera. I sent Daryl the whole manual about how to clean these suckers. It's from cooling the camera. We're going to be cooling the camera in stages. We go to minus 20. We're going to cool it in 5-degree increments. So we're going to go like 4 sets of cooling stages. Yeah. I see something else. Look out here. Are these in this galaxy? Is this part of a long, elaborate spiral arm?
I see it to the left, to the lower left, and below. I'm not sure if I see that or not.
Well, look at this. Looks like an H2 region. This looks like stuff. This looks like more stuff, and it looks like it's attached to this galaxy in some way. Hey there, Harold. Harold hears. What's up?
Yes, it's there.
Okay.
The image I'm seeing is from European Southern Observatory's Lucilla.
Okay, because it looks like it's doing this. Looks like it's coming out and going up.
It is. It's faint, but it is there.
Okay. It looks it. Nice. Nice. And this is only a 50-second exposure. If we did like a 3-minute exposure, we might be able to see that, but people watching would be bored. So I would do that when you guys aren't here, when I'm doing it by myself or with just Daryl.
There are a lot of H2 regions in this galaxy.
Excellent. Well, I'm glad we went to it, because I did give it short shrift the other night because it wasn't looking too good. But if you look where the telescope's peaking, it's actually kind of low to the horizon. So the fact that we're seeing it in this kind of detail is a testament to the air quality out there. you know. Sam S says, I see a box shape of stars below that object. A box shape of stars below the object. I don't know where you mean, Sam. I'm probably putting my cursor right through it, and you're saying, yes, there, but I don't see it. Again, these streaks are an artifact that I'm getting rid of. It's condensation streaks on the sensor. At least that's the best thing we have yet to explain it. This looks like a supernova. Is that really there?
A remnant, perhaps. Let me go back to it. I went on to M83.
Okay. I see lots of H2 regions.
Yes. Let me take another look. Okay, point that out again.
It's this guy right here.
Oh, yeah, that is on the image. Interestingly,
Okay.
it's red in the Lucilla image.
Is the Lucia image false color?
Doesn't say so. It looks natural to me.
Okay.
Yeah, it's quite red in the Lucilla image.
All right.
Let's say through a large set of mini filters over many observing nights, spanning several years. Nice picture.
Well, see, guys, now you have an idea of what it takes to get a real astronomical photograph. You don't have to. I mean, we get beautiful imagery in 20, 30, 40 seconds. But we're doing it in a way that gives you guys something to see right away. And again, no one else is doing this. There's nobody else in the world doing this. We're the only ones that are doing this nightly like this. I don't know, I think the whole presentation kind of is good, you know. It makes us feel good about what we're doing. We're getting a lot of good attention, you know, people are liking it. That's all that matters, you know. I want you to understand astronomy and understand things, phenomena. Not many are going to remember my string theory discussion a few minutes ago, but there might be that one person that will, who then goes to look it up and finds a whole new world waiting for them, for all we know. So, okay, we've got 13 here. We're going to go to 14 on this and move on. We're going to go back to Vesta. It's been about 40 minutes or so.
Yeah.
And we're going to go see if Vesta... Yeah, do give a thumbs up if you would. You know, if you haven't subscribed, why not do that? It's all free. And go here, SkyTourLive.com. That's our portal to all this. You can go see the pictures on the live active server database that's up there and see pictures from literally seconds ago. Up there now. Download them and use them. Sam S, I know, I wish you could point too. Because then I know what you're talking about. Okay, Izabela says, I'll remember the string theory, rings all the bells for me. Yeah, I mean, that's makes a lot of sense. Because if you think about it, everything's moving in the universe. Nothing is at rest. Everything has a vibrational frequency. And so thinking about the universe as a bunch of vibrating strings, you basically ignore the particles and just look at the vibrating energy from one endpoint to the other effectively. Yep. Okay. I lied. I'm going to go to 15. We're almost there.
This is a nice little spiral.
Yeah, I can actually see the structure very nicely now. That means we can bring it out and we do further processing even better. Okay, we're going to pause this and we're going to... what's the name of this galaxy now? Southern Pinwheel. It's a galaxy.
A southern pinwheel. M83 is the southern pinwheel.
Okay.
That's over in the spring sky, though. We've probably looked at it before.
I bet we have.
You know, galaxy season.
We have actually. We have.
It's on the border of Hydra and Centaurus. So that's over there by Virgo.
Okay. I will clear this now. And clear the stack. And go back to our 1 second and our night vision mode. Kaboom. Alright. Now in night vision mode, we're going to run back over and check out that asteroid Vesta. Remember this asteroid? This is the 3D print of Vesta that I made. John Sprott. Hey, thank you. Thank you, John. That's very kind. Thank you much. I'm glad that you're appreciating it. Okay, let's go over to Vesta one more time. It's over here somewhere. Okay, I gotta find it. Oh wait, I don't think I have to find it. I think it's over here. Here it is. Here we go, right now. There we go, right now. Okay, there's Vesta. Here we go. Now. You go now. You be here for an hour. Remember that? John Pinette. Okay. The telescope is going way over, as you can see. Hey, Science Bob. How's it going? I know Bob. Bob's a good guy. Hey, thank you, Bob.
Thank you, Bob.
That's awesome.
Cosmic ray, I was wondering that myself. It happens. Thank you again, John Sprott.
Well, thank you, man. Thank you so much. You guys, you don't know what that means. It's incredibly helpful. I mean, we're paying $110 a month for our internet out there, on top of shouldering the cost of the equipment and changes to the equipment. Just repairing things that go wrong costs us almost $1,000, and we don't have that money to waste, you know. Okay, well, here we go. If you look, all right, if you look right here, this is Vesta, and I can do a comparison with you because I'm prepared to do that to see if we see movement. Okay, so there is Vesta, and we're going to zoom in a little bit. Okay, so there's Vesta, and let's look at another image of Vesta, which I had, didn't I? Where'd I have it? Here it is. And I'm going to make that visible to you guys as well. Let's move this over a little bit. Move you out of the way. Move this over. I'm just prepping it, guys. Just 1 second. All right.
Okay, and the earlier image you have over on the left, Vespa's a little farther down. It's a little left.
Vesta is right there. Yeah, I want to zoom in on this.
Yeah, if you see the stars above it.
Yeah, it's clearly moved. Okay, guys, I'll show you now. You ready? Let's see if this works. Yeah, there we go. Okay, so here is our live image of Vesta right here. Okay, there is Vesta. All right, you see that star right there? Okay, this is the earlier image. That's that star, and here's Vesta. You notice how Vesta is at that angle to this star, and over here, Vesta is at a steeper angle to that star. So there you go. Right there, we're seeing the universe in its dynamic motion right in front of your eyes. We did it about 40 minutes ago, and in that time, Vesta has moved a little bit to the left. I mentioned, remember, it was going to be moving a little bit to the left, and it has. It's heading toward the east. Again, let's just do this. Okay, you can see that angle right there. Okay, right there. And then here, let me zoom in on it again with our live shot here. This is our live view of Vesta. Alright, so you can see Vesta earlier was just past the underneath of the star here, and here it's farther over from that star.
Yeah, if you make a triangle with Vespa and the Vesta, sorry.
You keep saying Vespa. You must
know,
want you must want that kind. You must want a Vespa.
The two stars to the right of Vesta.
Yeah, these two.
No.
Well, those are two stars. You mean these two?
No.
Okay.
The two stars closest to Vesta on the right.
Okay, that's this one. It's one of the
that
ones.
one, and then the one it's lower right there.
Yeah.
And if you look at the shape of the triangle between the earlier and the later picture, you can see that the shape of the triangle has shifted quite a bit.
Yeah. And it's just easy enough to see how here it's just passed underneath this star, and here it's even more beyond that star. So the angle has changed significantly. So there you go. The dynamic universe in motion, guys. And that's the way it works. Boom. So
Thanks for showing that, Mark.
yeah, I think that's pretty cool. I like showing the dynamic universe out there, because it's always changing, and we just don't notice it, you know? We just don't notice. Cosmic Ray, ignore that man in the red light. He sells snake oil in the daytime. Exactly. If you're not careful, I'll say that the Earth goes around the sun, too. Yeah, that's funny. Desert Dweller asked us before, Daryl. He asked about any comets. Are there any comets right now? I don't think we have any.
There are always comets out there. I don't know of any bright comets at the time.
I don't know of any bright comets that we have near us right now. Yeah. But hey, you know, I would say maybe. But, you know, the brightest comet is, the comets that we're going to see are going to look like just little tiny fuzzy balls, far less interesting than the galaxies that we've seen tonight. But Desert Dweller, not to fret. When we have some comets that are worth looking at, I promise you we're going to look at them. We're always looking for things that happen, you know. We have an all-sky camera, which is right here. Okay, which I'll show you. Okay, this is our all-sky camera. That's bird poop. Thank you very much. Okay, actually, so is that. That's a new one. It seems that the ball of that camera turns out to be quite an attractive roost for owls and other creatures out there, and then they poop on the dome and go away. But we're going to do a 12-second shot. This was early on in the night, and now here's the next one. Check it out. Wow, look at that. There's the Milky Way. All right. Now, you can't see it with your eye but when you're out there, but this is the lights of Phoenix 65 miles away. Right? But you can't see them with your eye. You just see darkness. But a sensitive camera can see it. Right? So, there we go. And we do have a cloud bank approaching, but it isn't here yet, so we're going to keep going. Well, there we go. Nice night. And so now what we'll do is we'll come back here, go to our wonderful planetarium here. And we're way down near the horizon. Saturn's almost set now, actually.
Yep.
So let's get out of this. And why don't we go check out Uranus? While we're doing planetary items, let's do Uranus too. And we'll see some of the moons.
How much we saw. The other night. The moons were more prominent.
Yeah. We'll see. As it comes in, you watch the dash, and the dashes that you see coming in. I think this may be it right here. Actually, that looks like it, yeah. How can you tell, Mark? Well, because you see these little dots around it. You can see the moons. But that's my theory and what it is too. But I'm going to come in here and center this up and zoom in and check. Okay, so this red square is our field of view. Okay, so we should see one star here and one star there. If this is Uranus, one star there, one star there. And then we should have a red one. Actually, that might be the one we're looking at. Okay. Let's go back in here. Yep, there's that. This star right here, slightly red. That one. Yeah, so then you move over to the next star. And then down to Uranus. And there it is. Ta-da! Okay, so what we'll do is we're going to move a little bit west. Pull that in. And then we'll go a little bit south of the... We'll go a little south here. A little north, actually. And then what we'll do is zoom in while we're at 1 second here and change our exposure to actually check it out. There you go. So you see we have what look like 2 dots here, 1 dot there. Let's go back now and see what we're looking at for moons. If we zoom in on Uranus now, let's go over here, center it up, zoom in. And there we go. We've got Titania and Miranda, Ariel, and Oberon. So sort of in a row. What's this guy? Is that a star? Yeah.
Oberon, Umbriel.
We have Umbriel. Let's get closer.
Ariel, Miranda.
Let's get closer. Okay. So now what we're going to do is take a photo. We're going to take a 4-second photo. That might be too much. But let's just do it anyway. See what we get.
If I remember right, the moons of Uranus were named after characters in A Midsummer Night's Dream by Shakespeare.
I think you're right.
Yeah.
There's Titania. Right there. Note the orange cast of Titania.
I think we noted that the last time.
Yeah. Well, I think that we did that with Titan too. But here, you see Titania's orange cast. And then we'll have Miranda. And then a star. And then we'll have Ariel to the upper right. So we'll have Titania. Is that the star?
Star.
And then we have 2 here. What 2 are those? Am I missing one? We have Miranda.
There's a little bitty one to Miranda's left called Puck.
I see that, but I don't know.
I'm not sure that's what we're seeing.
Well, it's a little itty bitty one, but I don't know. And this must be Ariel up here, correct? I think I'm going to take just a little bit longer exposure.
I think there's 2 above.
You know what I'm going to do? I'm going to drop
Also.
I'm going to drop our sensitivity down to 100 and take a 8-second exposure. All right. And look at that. because now we won't have as much noise in our image. It should be a little clearer. 8 seconds might be too much, but we'll see. And what do we got? Oh yeah, well, looks like it was a little too much. Not enough, rather.
A little color in Uranus, no?
Yeah. Let's drop it down to 4 seconds at 100 gain. Okay, now you can see the color of Uranus much better. Okay, and now we'll go to about 2 seconds. Now you can see, look at that. Now you see the color of Uranus quite nicely. All right, let's drop it even lower because it's even too bright. And I'm going to drop this down to 0. 0 gain. Now you see the color of Uranus. That's more appropriate. That's more the color of the planet. Okay, and this is like 1400 milliseconds. That's just 1.47 seconds. All right, now if we increase it dramatically, go up to, let's see, that's too much. We'll try 5 seconds at 0 gain, see what this gives us. I want to start pulling in the moons. Got to go more. We'll do 10 seconds. We'll double it. Hey there, Tim F. Woohoo! Okay, not quite enough. I'll increase the gain slightly. Go to 50. See what that gives us. Alright. This is what astronomy is. You work through the differences. Okay, this is 20 seconds at 50 gain. It's good to be able to go and do the gain because modify the gain. If you couldn't, you just wouldn't be able to photograph anything in any reasonable amount of time. All right, what do we got here? Okay, we're starting to get some stars. I'm going to increase gain now again. We'll bring the gain up to 150.
Uranus was discovered by William Herschel, of all people.
Mm-hmm.
It had been sighted many times before. John Flamsteed saw it on several occasions.
Mm-hmm.
Hipparchus saw it way back in the BCs. They thought it was a star. Herschel thought it was a comet because it moved, but he eventually figured out it was a planet. Uranus is bright enough that it's barely visible to the naked eye from a good dark location.
Mm-hmm. Okay, so this is our. This looks like a Gemini telescope image. Okay. There we go. All right. So let's see what we've got here. Let's zoom this histogram. Now we can play with the typical gain we have. Okay. This makes it very obvious. You can see Titania here. Definitely got 2 moons here. One of these is Ariel. This is Oberon. Huh?
No. Miranda there on the lower
Miranda?
right.
Which one's Ariel then?
The one above it, I believe.
Not this one. That's not Ariel. That's Oberon. Is Oberon over here? Over there?
Let's go look at.
Yeah, why not, huh? Instead of keep guessing, right? Here, we'll do this. Okay, let's go hunting for planet moons. Okay, it's Ariel up there, and that is why it's a little bit orange. Yeah, we're actually zoomed in too far for this scale. If we zoom out to the right scale, that's just a little too far. That's about right. So we have Uranus, and we have 2 in line. Now, it's weird because...
Miranda's the outer one.
Yeah.
And it shows Puck as the inner one, although Puck is small compared to Miranda.
Yeah.
And that is, what is it, Titania there at about 5 o'clock?
Yeah.
Titania, that is Ariel.
Yeah.
Just slightly right of above at about 12:30. That's
Right
Ariel.
here.
Oberon is farther up.
How come we don't see it?
I don't know.
You should see it. And this right here might be, this might be Umbriel. That might be Umbriel. Actually, it could be as simple as the fact that we need to go and say, I'm at 150, let's increase the gain to 250 and clear the stack and do this again. All right, so now we'll come back and we'll get this picture to come back again, and then we'll just modify it. But this is the planet Uranus. Here we go. Yeah, now we can see Oberon. If we come back here and again, let me just move this over. All right, let's do a comparison now. All right, so there's Titania. Is that Titania? Yep, Titania, and it's right there. An Ariel, right there, and then there are two objects here, and I only see one here. Makes me.
If you zoom in on it, the brighter one is Miranda, and the little bitty one next to it there is Puck.
Yeah, but that Puck is too bright.
Yeah, I know. You wouldn't think.
Because we got Oberon here, you can see it. We've got Ariel right here, you can see it.
Oberon.
No, Ariel. This is
the one on the left. Is that what you called Oberon?
no, this is Umbriel.
Yes, Umbriel.
Ariel, and then we
Ariel.
have definitely have Miranda and Titania. Miranda.
You might remember when River Tam spaced out on the commercial for the candy, whatever it was. She was watching TV, and there was a hidden message in the commercial, and it made her flash on Miranda. And the movie Serenity, the follow-up to Firefly.
Oh, I remember Serenity.
Yeah, that's what caused her to trip out.
Wow.
Miranda.
Well, there you go, folks. An exploration of Uranus in our solar system here.
So Oberon is the dim one up at to the upper left of Ariel.
No, Umbriel.
No, Oberon, the one that was above Ariel.
Oh, yeah, that's up here. That's Oberon. It's not dim. Okay, Ariel. If you look, they're kind of like it's weird. Okay,
Well,
maybe
doesn't. I mean, I think that's Oberon right there.
I think you're right. I think that's got to be Oberon. But you know what? It could be also. Here's the thing. It could be. It could also be that in my stellarium here, I don't have the stars loaded that would show us that these are stars. Like this is Oberon. There's probably a star here. Then we have Ariel. And then we have these two. And that can't be Puck. That's got to be something else. You know what? Stellarium can be wrong too.
No, say it ain't so.
Yeah. Well, anyway, that's cool. But we're gonna save this picture anyway because this is Uranus and it's actually kind of cool. All right.
Is your focus getting soft? Or are you zoomed way in? Oh,
I'm zoomed in at 319%. I'm way in there. So the fact that we have stars that are still sharply focused means that the telescope is focused and the guiding is great. Okay, we've stacked 11 of them, so I'm going to save it at 12. What you got? So 12, save exactly as seen. All right, and now it's saved, and so now what we can do is head up to something else now.
Thank you for sharing that.
Yeah, I thought it was kind of cool. Okay, now let's go to our night vision again. All right, back out.
Uber, all those moons of Uranus are named after characters in Shakespeare's A Midsummer Night's Dream.
Go
I don't
figure.
know what the naming convention was, but that's what they used.
Yeah. All right, and hello, weird guy. I saw you show up earlier, but didn't get a chance to say hi. Okay. Let's go. Let's bring up our gain. Go to 400. And let's set our time. Let's set our time, Robin, to 1 second. Holy whack-a-mole, Batman. There we go. All right. And now we're going to see all the many stars in the night vision setup. Okay, so now let's go over to our planetarium system here. I'm going to all right, Daryl.
Yes.
Anything is up for bids. Let's see. We're here. I wonder. We could try this and see if it's up high enough.
Pleiades?
Yeah.
Sure.
They're stunning. Might be... Well, there we go. We got them. And I think they're up. Oh, good, guys. We have some fun tonight. This is going to be good. Okay. The Pleiades, just over 400 light years away from us, are a cluster of B stars. Not O, but B stars. Very hot, young. And it's not just the Seven Sisters that you're familiar with. It's actually stars that are what am I doing here? Trying to get this to move. It's not moving. Okay, let's do this. We're going to turn off the live view and turn it back on. Oh. Okay. Interesting. All right, come back and we should be ready. And okay, hold on. We're gonna figure this out. Where's the camera? All right, got the camera in there. I'm gonna do this again. Well, it's guiding.
David Schmidt, I think James Dugan beat you here.
Yeah, he did. He did.
What happened?
I'm trying to see what's going on with the camera. I'm not getting a response from the camera. So I'm going to quit the camera program. started doing flaky stuff. All right. That was very strange. Now let's make sure it's still there. Uh-oh, that's what it was.
What's that?
Camera's disappeared again. Okay. Well, that's no good. I thought that's what was happening. The camera was in the process of flaking out on me.
Oh no.
Yeah. All right, well, what that tells me is that what I'll do is this. I'm going to, I will park the telescope, close down everything, and then I will come back in and see what happens. So telescope is still fine. That's okay. That's all right. It's just troubleshooting, just long distance. That's all.
Uh-oh, Reggie.
I'm going to reboot, and if it doesn't see the camera, then it means that this other problem that we've had in the past is back, and that's not good.
That cable?
Yeah, well, I replaced the cable, so that shouldn't be a problem. Okay, telescope is off.
Replaced cable a couple of times, didn't you?
Yeah, we're okay now. Okay, so I'm going to close this roof. You'll see the roof closed now. There goes the roof. All right, and we'll disconnect the scope. And quit this.
Bad telescope, bad.
Yeah, it happens. Okay, and this I'll quit. And this I will quit because we're done with it. And then these guys go down as well. And now I'm going to reboot this system. The restart may not provide us with the camera, and what sometimes happens is I gotta turn off power to the building and get power back. But for us, what that means is I don't have a way to do that. I don't have a way of getting back power to the building. Shutting it down, bringing it back on. I'm working on that because if I did, right now what I'd be doing is cycling power to the entire building. I know how to do it. I just have to build the circuit to do it. But we'll see.
Need a big red button.
I do, but one that then is still connected to the internet when we hit it. If you think about it, that's the problem, isn't it? Okay, I'm waiting for the building to come back. All right, it's back. Let's go see if we have our system back. What a pretty lighthouse. All right, let's come in here and right away let's jump in and see if we don't have it, then we're done for the night, and then I'll troubleshoot again tomorrow. Look, here's the camera. So we got it. Yep, camera's back. Okay, so what we're gonna do now, and it's at minus 18.6 Celsius, so we're still good. Are we still getting data? Oh yeah, we're still getting data. Okay, so I'm gonna drop this down now, and well, you get to see the whole startup process, guys. How about that? Okay, this is my startup program I wrote. I reduced it to a very simple set of functions. Yeah, I know that. And so next step is to bring my system here up, and so I'm going to do that. I don't know why I lost the camera there. That was problematic. Here goes the roof.
My tea is cold. Will you excuse me, please?
Yeah, cold tea is no fun. Okay, then we'll turn power onto the telescope and bring it back, and then we'll go to the Pleiades again. All right, and I want to bring this gamma down. I'm telling you, you gotta work the problems or they're gonna work you. Okay, and then this guy comes up. All right, and I've got this guy, and this is going to be over here. Sorry about the delay. Think of it as a commercial break. All right, and let's go over here and move all this out of the way because we don't need all of that. Here we are. That's good. And gear, and now let's do this over here. That is that. And now let's get our other camera, the one we really care about. Is this one. We'll minimize this to see it. Okay. We're taking our GPS fix, and we're all done, all set to go. So that means we can now connect the scope. And yes, okay. All right. And this is going to be about here. I'm going to reduce this in size. That's good. Don't worry about that. It's connecting. There we go. All set. All right. We're good.
Back.
We're good. We're good.
Shouldn't be drinking tea this late anyway.
I don't let anything get me anymore. You know, you could go crazy with this stuff. All right, that's over there. That's there. That's good. And we got that one and this one. Okay. Okay, next is our planetarium program. It'll come up probably already connected to the telescope. And it's actually, it's good to see. It thinks it's up there. It's not, which is good. I'll disconnect and reconnect. And reconnect. And then it's going to go to where it knows it is. Down there in Phoenix. Actually, it's in the constellation of Phoenix. All right. So let's first go to what's this?
Next, the furnace.
Yeah. Where did Galaxy just go? C6 NGC 1097. We did that before, remember? Isn't that
sure.
the one? Is that the one we went to? The one you told me to go to?
Oh yeah. Maybe
Oh yeah. Yeah, he did have me go to that one.
No, that was just fairly recently.
Yeah. All right. And let me bring up the camera right now. There we go. Okay, I have to just get rid of this. Okay. Let's get our night vision system back. There it is. Yeah. Okay, so that's good. I just want to adjust a few things. Let's get down to get this done. This is all stuff I do before I start, guys, so you get to see it all again. Of course, you don't get to see it because I do it without you here. I do it behind the scenes. We'll do it again now. That's the right ascension rate. I'm going to set the declination rate, which I found that 20 is ideal now. And so there. And then I got to come down here and turn off high precision so that we don't try to search for stars it can't see. And this is good. So then we just go up a few clicks. All right, and go into our status. Here we go. Okay, there we go. And now set our motion rate from max down to 16 times guiding speed. And we're going to just move the telescope west a little bit. All right, and then move it north a little bit. Okay.
This is an interesting spiral galaxy.
Yeah.
It's small, and I think we saw a surprising amount of detail in it the other night. There's actually a second galaxy setting at about 1 or 1:30 to the main galaxy.
Yeah, I was thinking that we'll image this. We'll image this while we're here, but it is kind of low. But we'll image it anyway, because we will get to the Pleiades after this, too. We'll run to the Pleiades right after this. Okay, so that said, let's get rid of these. Okay, and we are doing our thing, and let's go back to this and synchronize this with our field of view. Our field of view is 2 degrees across and 1.5 degrees tall. So let's synchronize it and let's have it center up everything. There we go. So now our coordinates in here are exactly the coordinates here. Everybody is aligned with each other. All right. And while we're here, let's just do a 35-second shot of this guy, and then we'll go to the Pleiades after this.
All right.
So live stack.
You want to change your gain, or are you happy where it is?
It's 350, so we'll be all right with that.
So you're running at 450 or something.
I was, but this is a small object, so we use the pixels and suffer a slightly fainter image, but we'll get more detail because it'll be less noise.
Very good.
I'm not planning on stacking a lot here. We're going to start zooming in almost as soon as we see the first image in 1 second. And now, bam. And we'll just do this. Look at that. That's cool. Yeah, see the orange? It's hitting the edge of the building. That's the edge of the roof.
It's a little early there.
Yeah, and so we can't do much more than this. But I'll zoom in just so you can see. What's interesting about this, okay, is that... Oh, I didn't even connect my focuser again. I got to connect the focuser again. What's interesting is you see this red here, and if you look right there, you can see the telescope is sort of leaning... you can see it's looking at sort of the edge of the building here. There's a tiny red LED on the camera, and the camera's inside this opening here, looking outward. Okay, but it's getting its information from inside. But on the back side of the camera, there's a little red LED for power. And that red LED is enough to put a red glow on the wood. That's how sensitive the camera is. You can see that. So it's really quite a good camera. This is a beautiful barred spiral galaxy. You can clearly see this classic bar.
And that dot up at about 1 o'clock is that's another galaxy.
Yeah, that's right. Okay, so Obviously,
Seems
this doesn't work because it's in the building, so I'm gonna kill it. But did you want to say something first?
like a silly place to put an LED, but I guess typical application would be behind the telescope anyway.
Yeah, that's true. Okay, this obviously is gonna not take us anywhere special right now. We'd have to wait a little while longer. Let's go into our night vision mode again. And now let's go where we're going before this all happened. Let's head up to the Pleiades. Because those are beautiful. Those looking really good. Oh, there's 1079. It's like, oh, there's this. Oh, there's that. We'll never get there. Yeah. There's the Robin's Egg Nebula. Look at Robin's Egg. Yeah, that's small though. It's a small planetary nebula.
Comet planetary nebula.
A what?
Called it a comet planetary nebula, whatever that means.
Maybe because it's greenish blue like comets and they're cyanogen. Uranus the river, that's where we are here. Amazing. Yeah, this is all pretty up here. It's good stuff. Yeah, and now
Uranus is a big constellation.
yeah, look what's coming. Here comes Orion. Orion's up, but it's not high up. But we can see the Merope Nebula and the Pleiades and the Maya Nebula. So let's just go there. That was fully up. So let's check it out. Here we go. You'll see the Pleiades come in. You can't miss them. You saw them before as we came in. And here they come right there. Look at that. Beautiful. Yeah, those are the Pleiades. We'll center it up here in a sec. Okay. Wow, really nice. Let's head west a little bit. Let's see where this is in our center point. Okay, we got a ways to go here. Let me zoom out. Okay. We'll center it up. Okay. Now we can get rid of this. Okay. So the Pleiades, as I said, B-type stars. A lot of these other brighter stars are part of the Pleiades cluster, but you're only familiar with the big hitters, you know, like Alcyone, Merope, Maya, Pleione, Atlas. What are the others? Taygeta. You know, you're only familiar with the main Pleiades stars, not noticing that, or not seeing that this is a cluster of young hot stars. And you'll see this haziness around it. That's not clouds or anything. Well, it is, but it's interstellar clouds. It's clouds of dark dust that is scattering the blue light from the stars, and so you see it. But let's take a 45-second photo. We're doing our stream, our guiding here, and it seems to be very steady. So here we go. 45-second stream, and we'll come out of this now, and the Pleiades will still be visible because they're very bright. And we'll jump into the live stack. Okay, and we'll clear this last buffer. And now, behold the beauty of these B stars as they pass through these minuscule dust particles, almost like fog, but the particles are way smaller than the water droplets that make up fog, thousands of times smaller. And it's not nearly as dense, but there's so much of it in the multiple light years across that we're looking that it looks like vast dense clouds. But here you go, right now. Ah, look at that. Now let's make it look better. Look at that. These are the dust clouds. Let's color correct. All right. Look at the dust clouds. It almost looks like a mistake. What's that? What'd you say, Daryl? Daryl? Uh-oh. Guess who is having connection troubles? Let me know when you're back. I hear him say hello. Alright, well anyway. Hey David Schmidt. I don't know if I got the say hi to you before. So these purple halos are the result of the system. You know, and so forth, and that's why those do what they do. But we're gonna, you know, we're gonna see if we get Daryl back here. All right, we'll call him back and see. Yeah, he's not answering. His machine must be down. That happens. Anyway, we're going to keep going here. These purple halos again, I get rid of those in the processing that we do. The Pleiades are these beautiful stars, and the thing is, the dust clouds that the Pleiades are going through could be related to the dust that we may also be sitting in as our Earth system with our sun. So these are vast dust clouds, and I think that is pretty cool, you know. Hey there, Cyclone. Cyclone says no questions tonight. Okay, he has no questions. That's fine. You know, and Cosmic Ray beating me to it. The Pleiades have thousands of stars, about just over 400 light years from the Earth. And when you think about it, the several thousand stars in the Pleiades, and it being 400 light years from the Earth, that's actually quite close to us on an astronomical scale. It's quite close, you know. So that's pretty cool, you know. And that means that the dust that we see here could very well be related to the dust that we're also in. We may be in the same dust, in fact, that the Pleiades are in. The dust, you don't see the dust out here. You don't even know it's there, but it's there. And what is that dust? That dust is from many supernovae over time. It was made in the atmospheres of the outer layers of stars. And almost like soot, carbon molecules, you know, carbon and carbon together. Silicon particles that attract ice to them along with the carbon, and make this beautiful foundational set of materials from which stars and planets can form, because there's certainly a lot of hydrogen out here as well. Let's zoom in and check it out. This is a beautiful one right here. This guy right here looks like a mistake, doesn't it? But it's not a mistake. This is called the Maya Nebula, and all these clouds and everything are associated with a cloud. Okay, here we go. Daryl's back. I'm going to give him a call. Okay.
Hello.
Well, there you are. Welcome back.
Everything's going flaky tonight. Thank you.
No problem. Just make sure you talk into your mic.
Okay.
All right, so we're on the Pleiades still, so we're still there. Look at
Share
that.
screen, please.
Oh, I guess that's a problem. There we go.
Thank you.
Yeah. Here, let's actually zoom out a bit just to show you the main players in the Pleiades here. So we go here. There's a lot of nebulae that are labeled in here. But let's go check them out. Okay. So the star out here this is Atlas. This is Pleione. All right. This star is Alcyone right here. Okay. And then over here, let's do this half of the Pleiades. This is Merope. All right. And Merope is then next to Electra, which is the star over here. Then up here is Maya. All right. And you don't see the name there, but it's Maya. And then you have Taygeta and Seleno. So those are the main stars that people are familiar with when you talk about the Pleiades, the Seven Sisters. You've also seen this emblem on a particular car, the Subaru. And that emblem was put there because it exemplifies unity. And they look at the stars here traveling together, unified in their travel through space. And so they chose it as their emblem for the car. So the universe affects down-to-earth business too. How about that?
When you look at the Pleiades up in the sky, most people see 6 stars in that little dipper shape. If you avert your vision a little bit, all of a sudden you'll see a patch of light about the size of a postage stamp at arm's length. And you're seeing the light of the bright stars, all the nebulosity, and all the dimmer stars in the cluster. Really cool.
Yeah, you need to, if you're in a dark sky and you use a big pair of binoculars, not a little pair, but a big pair, you might be able to catch the nebula too. It's slight. You might see the Maya nebula. You know, the Merope nebula might appear like a haze. You may see it, you may not. I know it was very hard. It was very hard to see it.
Yeah.
But we could actually approximate what it might actually look like. Okay, so here's what you look at. Here's about, this gives you an idea. Okay, you bring this way down. So you have a pair of binoculars, you're looking at it. You can see the Maya nebula, just a hint of it there. And the Merope nebula looks like a little bit of cloudiness around this star Merope here. Okay? And this is what most people see with the Pleiades, right? But then you start looking at it, you know, with a bigger set of instruments. Okay, and then you start to see other things, and the clouds start to show. Usually it's the Maya nebula and the Merope nebula that people will see first. And it bears out here when you see this. And then as you get better and better equipment, well, then you actually start to see even more. And then you notice things like, well, wow, these nebulae are connected. You know, and there's more out here. And there's something in here, and these are all connected. You don't necessarily see these connected yet. To see that, you've actually got to go further. And once you go further in, then you can see that there's a whole connection of dust that is literally being illuminated by these stars by scattering its starlight. It's the perfect scattering mechanism, these small dust particles, because the blue light from stars is what's being scattered, and the red light, okay, is allowed through, which is you know, what happens here on Earth. Okay, we see the red light being allowed through, and the blue light gets scattered, which is why we have a blue sky. Same process that makes these stars sit in a field of blue dust. Yep. Cyclone, what are you doing with the German?
I put him in a corner.
I noticed. What did he do wrong? What did he say?
He's speaking German.
Oh. And who timed out our other friend who had donated to us before?
I did.
What did he do?
He keeps speaking Chinese.
Well, we should probably learn, is it Chinese or Japanese? Is it kanji I'm looking at? What's he writing?
I don't know. Oriental. I suspect it's Chinese.
Okay. Well, Asian languages have their merits. I've been learning Japanese for a while. It did not look to me like it was Japanese, but I didn't look too closely at it. Actually, Japanese is very easy to learn. It's actually easier than English.
If I could ever speak Japanese, it would be with a hillbilly accent.
Think that you'd still be understood. It's not like Chinese where you have different tones. There's like 5 tones in Chinese language.
Right.
And depending on the tone, you can either call someone a horse or by their name. As I discovered. Yeah. And David Schmidt says, yeah, they may not understand that we're asking them to speak English either, and they might just be excited about what they're seeing. So I don't know. Language barriers are tough ones to troubleshoot. They are.
Hedrick, in this case, the dust and the stars in the Pleiades are about the same distance. The Pleiades are actually passing through a dust cloud.
Yeah. The dust actually, Michael Hedrick is his name. The dust cloud is actually not a something that's traveling with the stars. The stars are passing through it, and we know that because the stars are moving one direction and the dust is moving another. And so they're crossing in the night. Slow motion for humans, fast motion for galactic motion. So it's pretty cool.
Yep, there's a lot of dust clouds up in Taurus.
Oh, yes. Absolutely. Yeah. In fact, we should go look at the one of the clouds that's up in Perseus, actually.
I bet. Great minds think alike. I bet I know which one you're talking about, too.
The one I sent you today?
Actually, no.
Okay. You thinking about the lion?
I was thinking about the California Nebula.
Oh, California. Well, that's a beautiful. Yeah, that's a diffuse nebula. That is a nebula that's ionized hydrogen, so it's red. But I was actually thinking of the Perseus Cloud, so people can see the dark dust that's being illuminated by being silhouetted against a beautiful, soft, ionized hydrogen glow.
Right, sure.
David Schmidt says, Mark, can they adjust the readings they get back from the stars if the radio signals are passing through a cloud? Can they adjust the readings they get back from the stars if the radio signals are passing? I'm not sure what you mean by radio signals, David, on this. But if you're asking, are you asking actually, and mention it in the chat, are you asking if the starlight is being changed by passing through the dust? I mean, it's being slightly reddened because that blue light that's being scattered is blue light that's being taken away from the spectrum of the stars that are behind it. So the light reaching us is more red because some of the blue light has been stolen by being scattered. That's why the sun turns red at sunset, because the blue light from the sun is being stolen by the molecules and any dust particles in our atmosphere. And it reddens the light. We see this on grand cosmic scales, and it's called interstellar reddening. And it's something actually I had to take into account when I was doing photographs of the sky in the big observatory, because we cared about interstellar reddening. We had to calculate the reddening of the stars we're taking pictures of, because I was doing something called photometry. I'd have programmed stars and I would take photon counts what the photons were coming in. But those photons were diminished a little because of reddening. I had to calculate how much they were diminished and correct for that. And that wasn't the project. That was actually just to get good data on the stars. So it was a photometric project that was just reams and reams and reams of resultant work. In the end. I forgot about that.
It's not telemetry so much. It's just they analyze the spectra of the stars to determine composition.
Oh, I see what he's saying. Yeah, I know what you mean. The spectra of the stars, and I'll be able to show this better once SkyTour East is back up. That telescope behind me is going to have a spectral system on it, so we can actually look at these stars and look at their spectra, and you'll know exactly what you're looking at. You'll say, "Oh, look at that! It's got all these bumps and valleys in it, and those bumps and valleys represent different elements that are being absorbed and emitted from different stars and nebulae." We call the Orion Nebula, for instance, along with other nebulae like it, we call them emission nebula. Why? Because they emit light at the wavelength of H2, that is the hydrogen alpha line, and that is those emission nebulae in a spectrum are going to show up as these bright peaks at a specific spot. Now, if that nebula happens to be coming toward us or moving away from us at any significant speed for some reason, then that spike will be shifted. If it's moving away from us, it'll be shifted toward the red end of the spectrum, if that way's red. Okay? If it's coming toward us, then that peak will be shifted toward the blue end of the spectrum. And the actual line should be, say, here, but it'll be shifted one side or the other depending on whether it's coming toward us or away from us. That tells us the speed of things moving out there in the ether, out there in space. It's really just amazing. Okay, we have... I'm just so amazed at the guiding here. For 45 seconds, nothing is off at the slightest. And this is a 17-minute, 15-second photo of the Pleiades. And I think we're good with this last 24th frame. So we're going to pause this now. That sets us at a full 18 minutes. And then we'll name this as the Pleiades, which is also Messier 45. Okay. All right. And we'll save it. And save exactly as seen. All right. And now we can get rid of this and go back to our night vision view here.
And sure, do the Lion or one of the nebulas you had in mind.
Well, you were talking about the California. That's really pretty, but yeah, I'd like to go visit. I'd like to go visit the Perseus Cloud first, if I can.
Sure.
Let's see if it's in here as this. What was the name of it? I'll just find it.
I'm here, David. Can you hear me, Mark?
Can I what? I hear you.
Hear me?
Yeah.
Okay.
Yeah, you're going through. I'm watching you on the output in the broadcast. You're moving. You're out there.
Okie dokie.
Okay. This is where we're going next. This is right near this. It's actually a very spectacular location. It's called the Perseus Cloud. It's a dark cloud of gas and dust. And you see it almost immediately when we come in here. You'll notice there's like a void here. What's going on? And then there's a bright reflection nebula over here that you'll see, but then there's all this dust in here. And we're just going to move it up a little bit. Here we go. Hey there, OG Skywatch. How are you? go over a little. I think.
Okay. Mark.
Yeah.
OG Skywatch had a question.
Okay.
Can cosmic dust be used as a fuel source? If so, is there enough cosmic dust to power a self-replicating probe across the galaxy?
Ah, the von Neumann machine. Well, cosmic dust is made not of hydrogen. It's actually made of carbon and silicon. So carbon is a fuel byproduct, right? Carbonized stuff. When you burn something, it becomes carbon. In many ways, there's carbonized stuff that you get as a result. But you also you have silicon. Now, on the surface of the dust, you're going to have ice particles. Those ice particles might be usable if they have some type of a combustible material, but the only kind of fuel source you want is something that's going to be somewhat advanced. You know, if you're looking for solid fuel rockets, for instance, I don't think that the interstellar dust is going to help you.
Yeah. If you had a spacecraft capable of interstellar flight, you might use what's called a Bussard ramjet. It's kind of an old idea.
It is, yeah.
If I remember right, they rarely mention them, but at least maybe in some of the early Star Treks, I want to say they talked about Bussard ramjets.
Well, maybe. I don't remember.
Yeah, a long time.
Yeah.
Bussard ramjet.
Yeah.
They would project a field in front, and they would be scooping up interplanetary, interstellar hydrogen and stuff, and funneling that into the engines.
Okay, this is the reflection nebula I was telling them about, and I'm gonna move up just a hair more. Okay, this is good. Okay, now we're gonna get our guide star. So you'll see it searching 11, 12 seconds, 14 seconds. It finds it. Meanwhile, I'm going to do a 45-second timer on this. All right, we're guiding now. I'm going to wait for it to stabilize. Okay, we're stable. And now I'm going to say, off we go. And now our clock is ticking. We're underway. Into our stream we go, into our live stack, I mean. There's our Pleiades from last time. It's up there, saved, I hope. Yes, it is. Alright. And what I'm going to show you now is one of those dark dust clouds, which basically is the origin of stars and life in the universe. You know, these dark dust clouds are where it's at. This is where it all begins. It's where stars are formed. It's where planets are formed. It's where we were formed. In fact, the dust that surrounds the Pleiades may be part of the dust within which we were formed. All right, here we go. There you see it. That's the beginning. Now I'm going to take this guy, move him out of the way. And I'm going to remove the telescope from the view for a minute. Come over, there we go. And zoom in here a little bit. Okay, you can see the reflection nebula there. That's the halo ring from our telescopic system. And now what we'll do is do an adjustment here to show you what's really going on in here. Color correct. All right. Well, this is that cloud. All right, and it's actually pretty extensive. It's all throughout here. It's called the Perseus Cloud. Can you hang on a second while I go get something to drink? I'll be right back.
Sure.
I'll be right back.
Cyclone, my mistake. Click on the three dots. Oh, okay. Yeah, if you're not a mod, you may not see it. Give me a second. I'll go dig up my channel.
Appeared from out in the dark nebula. All right.
Cyclone, I don't see my channel. Sorry. It's not active. I haven't posted anything here in years. Looks like David found it.
What was this? Your YouTube page or something?
Oh, Cyclone wanted to know what my YouTube channel was.
What is it?
I don't know.
Huh.
I can't find my own channel now. YouTube has changed stuff around. David, if you see it, post a link to it.
So Daryl can have it again.
Yeah. There's nothing new in there. I don't remember adding anything in a while. Yes, David. Thank you. Looks like there's nothing there now. Oh well. Thanks for trying.
Let's go.
Well, that link that was put in there was actually a link for Terran Marie.
Not for me, it wasn't.
Okay.
The one David Schmidt posted?
Yeah, I thought that was okay. Maybe it was the link wrong. Okay.
No, that's my.
All right.
That's my home page at YouTube, I guess. There's really nothing there.
You don't have any videos?
Oh, there's stuff in my playlist, stuff in my channel, some of my favorites. Tells me a little about me, tells you a little about me.
Okay.
That's about it. I haven't added to that in a while.
Okay.
Sorry for the distraction.
Not a distraction. It's fine. Okay, I'm gonna try and tease some more data here out of what we're looking at. Oh, look at that. Actually, let's do this. See what's really back here. Oh, look at that. So that's what's really here, right? And let's color correct that. There we go. And let's bring it down to a more proper level. Look at that. Okay, so this is what I'm talking about. This is the seed of life in the universe. These clouds. It's in these dense, cold regions. By dense, I mean about 30 atoms to 50 atoms per cubic centimeter. Right? Consider there's 100 million atoms in a cubic centimeter of air. Okay, there's only about between 10 or 30 or 50 atoms, depending on the density, in these dust clouds, and they're very, very cold. You know, the dust particles themselves are very cold. They're sheltered from the radiation of stars nearby because of the density of other material around it. So it's in that cold dark where all the action happens in the universe. It's how it starts. It just takes a few particles to be close to each other that come close to each other. And now there's 3. And those 3 are more than the 2 out here. So those 2 are attracted to these 3. And it keeps going until now you have 5, then 20, then 1,000,000, then 1,000,000,000, then 1,000,000,000,000,000,000 particles. And thus a clump of matter is born in the universe, from which either a star can grow and wink into existence if temperatures in the middle of that compressed cloud get high enough, and if it's made of hydrogen, or planets can form, or both. Planets can form going around stars in the accretion disk that forms around the star. But this is known as the Perseus Cloud. It's in Perseus, as we said. Izabela asks a question. The dark nebula always look like they're in the foreground. Is it possible they're actually behind, but are so dense that they are visible through the nebulae? Well, I'm not going to say you're wrong on that, but what I will say is that at the very least, we know that there's dark nebulae that are interspersed within an ionized cloud of gas. And we can recognize that and see what it does to the light coming to us from that dark nebula. But I don't think we're gonna. I don't think we see. I don't think that we're gonna see that dark nebulae are actually behind there, behind the stars, because as you can see, you can actually see that this is a bright cloud. This cloud of dust is hiding many stars like this all around it. It's definitely hiding the stars behind it. The other thing is, when you look in here, if we zoom in, you'll see that the stars in this cloud are very red. And I talked about this just a few minutes ago. Inside the cloud, the stars appear redder than they do outside the cloud. Why is that? Is it because there's only red stars inside the cloud? No. It's because the cloud is full of this dust, which is doing what we call this interstellar reddening. It's scattering the light from the stars and the blue light and allowing only the red light to come through. In other words, we're seeing sunset for the same reasons we see sunset on Earth. These stars are all in a sunset mode forever, as far as humans are concerned. Beautiful cloud. We processed this, got rid of the noise and the color, and this has become one very popular image.
Nice little star cluster there in the upper left.
Yeah, that's correct. You're right. There's a star cluster here. And as you can see, it's embedded in this dust, and it's scattering the dust is scattering the starlight. Okay. Like a little blue nebula. There's one right here, too. Yep. And Fantasy...
Maybe those streaks are really there.
And Fantasy says, I always drop in during an amazing shot. Oh, yeah. What Daryl's not telling you is that these streaks that you're seeing here, these streaks are an artifact on the camera from a condensation problem inside the camera. So next time I go out there, I'm going to be taking apart this $1,000 camera and digging through it to clean the components that have these streaks on it. And then I'm going to, there's actually desiccant tablets inside the camera that I have to take out and cook in a microwave to get them ready to do this again. And then I'll put it back together all cleaned, and I'll have perfect images again.
The condensation is no longer there, correct? I mean, but it was there and it left the streaks.
Yes, here's the thing. Okay, yes, this is in the desert. It's at around 2,000 feet in elevation. However, it's not like it doesn't rain out there. But when it rains heavy and hard, and it's a muddy mess. When you try to drive out there after a rainstorm, and your clean car is going to have mud that's caked on it, and you actually have to use a tool to pry this hardened mud off the car. You can't just wash it off. It's not going to come off. It's hard pan. It's caked on, and you got to knock it off with a hammer and a screwdriver in some places. I'm telling you, I cleaned the Jeep, Marianne's Jeep, when I took it out of the desert, and let me tell you, it wasn't easy. That stuff it's like cement.
So like you need a pressure washer.
We had a pressure washer. It wasn't doing it.
Huh.
Yeah, I had to knock it off with a tool. Sam S. says, Mark, have you published any work on nebulae? The only stuff I've done on nebulae, Sam, is here in SkyTour LiveStream. But I think the next book is going to actually be a book on dark nebulae. And it's going to talk about the origins of life in the universe and how dark nebulae are extremely important to the factor here on how life evolves in the universe. Consequence Ray says, do not cook in microwave, heat in the oven. Well, they say 2 minutes on medium for the desiccant tablets for the camera. And, there's 6, 8, 10 sources I've been looking at online that all say the same thing. And the ZWO people say the same thing. They don't say heat it in an oven. But I guess you could do that.
That's what I thought I saw. And the directions you sent me was, they said put them in the microwave.
Yeah, 2 minutes.
Yeah.
I mean, they're going to be very hot, which tells you that a lot of the water was boiling out of them. That's all microwaves do is boil water.
Yeah.
That's all they do. They have a special relationship with the water molecule. Yeah. All right, we've done 19 of these. This is one of my favorite nebulae too. It's really pretty. Let's just
Gonna do the lion next, you said?
I was thinking of it because it's really such an amazing location. It's 2 Wolf-Rayet stars.
Uh-huh.
Yeah.
Excuse me again, please.
Sure.
Be right back.
But there you go, folks. That's the Perseus Cloud. And the Perseus Cloud is a location where, get a telescope back. It's a location where, future stars and planets are being made, being built. Deep in here, there's probably a lot of young stars being formed in there. Hey there, John G. Outrageous. Okay. Anyway, I'm going to do this here. We're going to say the Perseus Cloud. This will be the PER Cloud. And it's going to be a DN for Dark Nebula. Okay? So we'll save that, and that's going to go up there to the site. Save exactly as seen. Okay. Now we can clear that and go back to our night vision mode again. Here we are. Okay. let's see what else we have for similar fun times out here. That's the Perseus Cloud. What is this guy? Crystal Ball Nebula, yeah. That is a very beautiful nebula. Daryl asked for this earlier, so we'll go there. This is called the California Nebula. This is the exact opposite of the Perseus Cloud, okay? Which I'll remove that name now. Come here, you. Don't need that now. This is the California Nebula. And this is what's called a diffuse emission nebula. Again, ionized hydrogen gas, literally turned on by a hot star in the region, which I'll talk to you about in a sec. All right, let us first just doing the bookkeeping here. All right. Alrighty. Okay. All right. So now we'll move the telescope a little to the west, and you'll see the nebula come into view. Oh, good music for this. It's a hot, deadly region. This is Menkib. This hot star, and let's talk about Menkib for a minute. Menkib is an extremely hot star. It is an O7. It is among the hottest stars in the universe as an O7 star. And as an O7 star, it is pumping out much of its radiation in the ultraviolet, which is just what hydrogen gas in the interstellar medium is going to react to. It's going to take that ultraviolet light. The electrons in the hydrogen atom are going to shoot off the atom in an ionization maneuver, and then spontaneously come back into the atom. And as they do, they're going to release red light, which you see right here. As we look at Menkib, you're going to see this curved front right here. Menkib is literally carving the front of the nebula with its powerful skin-searing radiation. So let's take a look at what Menkib is doing.
You did go to California.
Yeah.
I wish they all could be California nebulas.
I was telling people that we're going to go see what Menkib has done to this nebula with its face-searing radiation.
That's one big honking bright star.
Yeah, it's an O7.
Yep.
So luckily, we're safe in our spacecraft here. A good enough distance from Menkib, which the distance of Menkib is something in the order of, where are we looking here? Well, I get a parallax, but I don't have a, oh yeah, okay. About 1244 light years. Wow, look at that. That is beautiful. And let's actually process that a little. So Menkib is carving this whole front of the nebula with its radiation. And it's literally blowing this material with its stellar winds outward, and its radiation is ionizing for several light years. These stars are not to be messed with. Now, Menkib's fate, on the other hand, that's also something that it can't ever escape. Its fate is to go in a big supernova when it finally does go. Like a dark water. Yes, I don't know what our Chinese friend was trying to say. Sometimes the translation programs don't even work. It depends how well organized they are and detailed they are in their vocabulary algorithms. Look at this California Nebula. Look at that. Named because of what it looks like, as you can imagine. Wow. And then also right down below here, we have what?
Oh, I was just reading about Menkib. Intrinsically 12,700 times brighter than the sun, but if you add the ultraviolet and light from other wavelengths is included, its total luminosity is 263,000 times that of the sun.
Sounds right.
That is big and bright.
Yes. Okay. I was talking about this before, the Crystal Ball Nebula. It's small, but it showcases O3. Wow.
Taryn, we looked at this the other night. I thought it looked like a dragon blowing fire out of its mouth.
Cyclone says, is there a nebula named Maryland? No.
Yes, David. The eye where that dark spot is, his mouth is just below that, and you can kind of see the dragon's mouth and lips, and the stuff at the lower left is the fire coming out of its mouth.
Izabela says, Marc, any development with the new location you'd like to share? As some of you know, we have two observatories now. We have the eastern one being rehabbed, so it's down at the moment, but it'll be up and running with a vengeance soon. And we, of course, have this one. The consensus among those of us running things at SkyTour LiveStream is that we are going to actually have a third observatory now. And the new system is going to go there. And it's going to be a very different location. It'll still be in Arizona, we think. But it looks like it's going to be down in southeastern Arizona. And that's going to be a location that will afford us a few things. Number one, this location, we have hundreds of clear nights a year. That location, we have as many. And here we have a fair amount, not as many as either of those other two. So at any one time, there should be no reason why we can't stream. One of the areas is going to be clear. And that still doesn't take away from the fact that we want a Southern Hemisphere observatory. So we're actively working to try and find a location in the southern hemisphere where we can put an observatory. Yes, this is Menkim right here. Minus the purple halo, which is the camera artifact. Izabela says, is there a monsoon in that place too? Well, you have a rainy season everywhere. So, yeah, there's like a monsoon. But I will say that it's more desert in this next location than where this is. And this is in the middle of the desert. This is in the Sonoran Desert. And this desert down there is more arid, actually. It's actually pretty close to the Mexican border, actually.
Yep. Yeah, I visited that area a long time ago. I was a kid. We didn't go to Tombstone, but we went to Old Tucson, I think they call it.
Okay.
Where they filmed a lot of Western movies.
Yep.
And we went to the Desert Museum down there, which was a really cool place.
David Schmidt says, what about security? Southern Arizona is not exactly safe. Actually, the site where actually Marianne went looking, the land she was looking at, there was already 3 other observatories on the site. Okay? And you'll be amazed, 2 of the 3 buildings look exactly like the SkyTour LiveStream building. So, same thing, wooden-based building with metal sheeting and metal clad. So, it's a pretty common style that, I came up with it out of my head with the metal sheeting coming from people, that, discussed putting metal around it in case of fire. So I think it's pretty cool. And Sam S says, will you be able to do a dual stream from both locations? Sam, I will be able to stream from all locations simultaneously. That's the coolest thing. Now, another important thing that Izabela asked is, what about the maintenance? No one will be able to get there fast. That is correct. That is why it has to be a very, very robust system that can sustain itself. The system that goes in there is not going to be any system that's prone to any potential failures or any potential accidents. It's going to have to be, well, we already know what we want to put in there. It's going to be probably a Celestron system, right? But we're looking at, and now that we know we're going to do this in a new building entirely, at least that's a thought. We're changing our whole plan on the instrumentation, but we do want to keep it similar to what we have, and that is very important to keep it similar to what we have, because we have to do comparative studies, and to do comparative studies you do 2 different sets of equipment. You got to use the same type of equipment. Cyclone says, are there different types of black holes? Well, that's the nice thing, okay? Black holes can have many different masses, but the effects of the black holes are pretty much the same. So, we know that only certain size stars, when they collapse in a supernova, can become black holes. So we know the minimum mass that a black hole can have. We're not so sure about the maximum mass, because those are surprising us as we're finding out. But generally, there's no black holes, for instance, that do crazy things that other black holes don't do. There's black holes that are odd, but within the understanding of black holes, there's nothing out there going, that's a black hole? That can't be. Look what it's doing. We don't see anything like that as far as I know, to answer your question, Cyclone.
There are so-called stellar mass black holes. There are supermassive black holes, and sort of, I guess, what they call intermediate mass black holes. If I remember right, they were having a hard time finding those.
Yeah, the supermassive black holes, of course, are not the kind of black holes you get from a collapsing supernova. It could be that a collapsing supernova created a black hole that then gobbled up other stars and grew in size. And let me point out another thing too, which makes people crazy. They talk about a black hole having a singularity inside, right? What does that mean? And they'll tell you it's an infinitely small point. Everything is crushed to an infinitely small point. That's not true. That's not at all true. Okay, what's true is the black hole's gravitational force acts as if it's from the center of a tiny point, just like the Earth's gravity acts. Okay, so if you feed a black hole mass, guess what happens? The black hole grows. Okay, the mass determines its radius, and the radius determines where the event horizon is, where the point of no return is. The more mass, the farther out that event horizon goes. So it's pretty interesting how black holes grow, and that radius is called the Schwarzschild radius. You can calculate it. You know, how big is the radius of a particular black hole? Okay? And so the math all works the same for black holes so far as we know. But black holes can be very different masses and sizes. Okay, Cyclone also asked a really, really good question. Galaxies look stationary, so why do scientists say that they rotate? Because they do. Next question. No, I'm just kidding. The thing about galaxies is, you know how they have spiral arms? It looks like pinwheels that are in the process of winding up, right? Well, if they actually wound up, then by now all the galaxies would be wound up into a tight ball. But they're not. So what's happening? Well, what's happening is their rotation is occurring. They're rotating like as if they're fixed disks, like they're rigid disks. The outer areas are rotating faster than we thought relative to the inner areas. And there is what's called differential rotation. The inside does rotate faster, and the outside does rotate slower, but it's way faster than we thought. And that's why the spiral arms are gently sloped outward and curving around like that, because there is that differential rotation, but not enough to wind up the galaxies. All right, which is very interesting. It's an interesting finding, and that semi-rigid rotation of the galaxy's disk was a puzzle for a long time. And then someone said, well, what if we envelop this galaxy with a mass with its own gravity that we don't understand? So just like a big cloud around the galaxy of this additional mass. Could that account for a galaxy spinning in a nearly rigid way with just this little differential rotation? And the answer was yes. And that became the concept of dark matter, and why dark matter came into the picture. It's called dark matter because dark meaning we don't know what it is. It's not normal baryonic matter, made of the typical atoms that we see. It's made of something different. And if it exists. Now, that's a whole different thing from dark energy. That's a whole other thing. Daryl doesn't like dark energy. But I see the case for dark matter. I actually understand and question the existence of dark energy.
Humbug.
Exactly. Okay, we're good here with 22 stacked on the California Nebula. Remember, go to SkyTourLive.com and then you scroll down and it says, I want to see cool pictures, and it'll take you right to the server that offers these up for you to take right there and put on your machines for free. Put them as backdrops, whatever you like. All right, we offer these all for free. Okay, 23 stacked there, that's good. I did the wrong thing. I'll do this now. All right. Yes. I was about to do it and I didn't. All right. Okay. So we're going to save it. And save it again as seen. The first one is the astronomical fits format. The second one is the ping format. You can just double click it and see this image just like this. That's for you to do if you want. Okay. All right, we have one more object to do tonight. And that is this guy right near this. And let's go back to our 1 second. So I showed you a dark nebula. I showed you an emission nebula. Now let's show you what it looks like when an emission nebula is sitting inside a dark nebula. This is a cool object you're about to see. Alright, let's get rid of the stack. I've said this before, the universe is my cathedral, and I absolutely love looking at this night sky. It means a great deal to me.
So where are we going now?
We're going to the northern Trifid.
Huh.
When I was 9 years old, I looked up into the night sky from Plainville, Connecticut, where I grew up. And I said to myself, I want to know what's out there. I want to be part of whatever's out there. I want to know. So, there it is. I started studying astronomy. And I ended up getting a degree in it because I knew at age 9 I was going to go to school for astronomy. And I did it. And I went on to graduate school in computer science. And ended up realizing that the computers and being able to number crunch like that were how you were going to figure things out in the universe. And sure enough, that's all you do now. That's all there is. And the data comes in and you crunch it with algorithms. And I love it. There's so much you can do. And I'm simplifying so much of it. I'm sorry. But it's really cool. All right. So this is called the Northern Trifid. Let's make sure focus is still good. That looks good. All right. You're going to see dark lanes in here and dust moving all over. You see how the stars seem blocked by something? That's because it is. There's dark nebulae and emission nebulae right here. This star formed inside the dark cloud. And you're going to see it. You're going to see the cluster and what it created. Not the cluster, but the stars and what it created. Okay, this will be a 45-second shot. Off we go into the wild dark yonder. So we left off at the California Nebula. And before that, the Perseus Cloud. And now we're going to see the Northern Trifid Nebula, which is a beautiful location. Cyclone says, what do the terms magnitude, obscuration mean? Okay, well, magnitude is the brightness of the star. Magnitude is what we say a star is a certain magnitude. For instance, Vega in the summer sky directly overhead, magnitude 0. Negative values are very bright. Positive values are dim. Betelgeuse, 0.58, roughly. Rigel, curiously brighter. Yet Betelgeuse is considered the brighter star because it's a variable. Sometimes it's brighter, sometimes it's fainter.
Well, Betelgeuse is the alpha star.
Yeah, but it's not the brightest star all the time.
Right.
Rigel is brighter at times. Well, here you see now, okay, in the first shot, you can see this beautiful red nebula, this star-forming region, inside a ball of dark nebula, which seems to go down here, and it does, and up here, and it does. So it's really interesting how this works. And this is, again, called the Northern Trifid Nebula. Called the Northern Trifid, kind of like the Southern Trifid, because it seems to have these dark lanes in it that divide it into 3. So it's very, very nice. let's do this. Let's let it process itself here. Okay, so we're gonna pull this back down a little bit, like this. All right, let's see how much is in here. All right, so now this is going way too much, but it shows you, okay, it shows you the dust in here. See all that? It's like they're arteries in space, and this is a blood clot. So, that said, we come back down, and now we'll see if we can pull out more detail in this. Oh yeah. Okay, let's color correct. There we go. Very nice. All right. And this would be called an emission nebula, because if you looked at this with a spectral system like we have here that you'll see when we finally get it set up, you'll see an emission line for hydrogen alpha coming out of the center of this nebula where it's red, well, orange. It looks orange to your eye right here. It's kind of a reddish orange area. Cosmic Ray says starting salary for astronomy job in the field's about 30,000. Well, yes, if that's the only value you have, yes. But if you have a personality and you can educate, then you can actually do more. And it's what I've leveraged to do that. I think that people appreciate learning. You know, I've actually encountered very few negative comments about what we do. The only one that's ever said negative things about what we do is someone that was actually envious of what we were doing because they wanted to do it and they couldn't. I offered, but they didn't want to hear it, so I don't know. See, we see the emission nebula here, but look what's up here. That's a reflection nebula. That's one of those nebulae where these dust particles in here, there's all dust in here along with the hydrogen gas. And this is the part that actually the star winked on in here and ionized hydrogen for some radius around them. And this is an area where the stars are just illuminating the dust. It's pretty cool. John, what's he talking about? Temperature and surface area. Combination of the two. What is that related to, John?
I recommended he take a look at the Hertzsprung-Russell diagram a while ago. He was asking about how to put it. What determines the star's energy output? I'm getting multiple answers, although I thought it was mass.
Well, he's right. It's the mass. Very large mass stars are going to have a very, very high energy output because there's more of them. more of it. And higher mass means higher core temperatures. So a star with a higher core temperature is going to fuse a lot of hydrogen into helium very quickly and go beyond that very quickly. And start shell burning on the outside, and then that leads to a very rapid demise, typically. They burn bright, but boy, their lifetime is shortened. Right? It's like the brightest candle, right? The brightest candle has the shortest life.
Yeah. And big blue supergiants, they age very quickly, and when they start running out of hydrogen, they start turning into red supergiants.
Yeah.
They swell up in size, they get cooler, but they're still great big stars.
Well, the core is very hot still, but they swell, and as that gas that used to be closer to the star that was hot and blue, as it moves away from the star, it starts to cool, and it becomes white, then it becomes yellow, and then it becomes orange, and then red, and then because it's not as hot the farther away it gets from the star, and thus that's your supergiant stage. Now the way they get there, okay, is they burn hydrogen into helium, they fuse it into helium, but then when they use up all the hydrogen, they start to contract because the outward pressure can't handle it anymore, because they can't fight the pressure to collapse. The outward pressure wasn't there anymore of radiation out, so the star begins to contract, and as it contracts, it gets hotter inside. As it gets hotter, new things can start to fuse. Now when it reaches 100 million Kelvin, then it can start to make helium into carbon, and then after that you get carbon into nitrogen and oxygen and so forth, all the way up to number 26 in the periodic table, which is iron. But iron can't go any further. So that's the end point. And the biggest stars get iron cores in their throats and can't do anything with it. So when it finally runs out of that last fusible material, in less than a quarter of a second, the core of that star just shuts off and collapses. And so all that material in the core, which is about the size of the Earth, collapses. And as it collapses toward the center, the rest of the star follows. When that stuff in the center hits the core that's immutable, the iron can't go anywhere, it smashes it with unbelievable amounts of pressure and rebounds off of it. And now it's starting to head out as the rest of the star is still coming in. And that outward motion, coupled with the inner motion, shreds the star. And that's what we call the supernova. It's called a core collapse supernova.
Big bada boom.
Type 2. Yeah. That's the one, there's all kinds of ways stars die, right? That's the core collapse is one. You also have the one where there's a binary star system, and one of the stars evolves to a red giant and then shrinks to a white dwarf. Then this star eventually goes to a red giant. Well, when that happens, they might be orbiting close enough so that as this gets to a red giant, gas from the big distended atmosphere of that red giant could leak through the center of the common center of rotation and deposit on that white dwarf. And a white dwarf is a white dwarf because it's no bigger in mass than 1.44 solar masses. That's an immutable number, okay? It's called the Chandrasekhar limit. And that limit, once passed, can spell doom for a star. And once that white dwarf has more mass from the bigger star bleeding onto it, if it's not 1.44 masses, it's fine. It could end up fusing spontaneously all that hydrogen gas on its surface, and then you get what's called a nova, a flare-up. And then once it's gone, the star goes back to acquiring stuff again from the red giant and does that flare-up every so often. But sometimes, if that mass starts moving onto the white dwarf and exceeds the 1.44 solar masses before any kind of flare-up occurs, then we have a big problem. Then you're going to get the spontaneous fusion, and then you're going to get a total destruction of that white dwarf star, and you get what's called a Type 1a supernova. Now, what's interesting is those are candles to us. When we see a Type 1a supernova, they look the same. They look the same no matter where we see them. So we know how bright they are. We know what their intrinsic brightness is. We know how long they're going to last. And thus, when we see a Type 1a supernova, which we can see in the spectrum of the star, we know how far away it is based on its brightness. And that's why they're distance candles for us. It's just a amazing, absolutely a cool discovery. This is looking nice, huh?
Uh-huh.
Let's see if we can pull out some more detail. We've got 16 stacked here. Let's go a little nutty here. All right, look at that. Look at that. So you see this beautiful tendrils I told you about of dark brown silica carbon-based dust in here. And then you've got that one central nexus where a star or more than one star formed and is ionizing this here. This is stunning. Let's see if we can actually pull that down just a bit more. How about that?
The Hertzsprung-Russell diagram. What is it? Luminosity scale on the left and mass on the bottom.
Color. Color temperature. Yeah.
Right. Okay. Color temperature. You're right.
Yep. And that's why when we say OBAFGKM, well, the O stars are hot and blue, the B stars are blue, less blue, and then the A stars are white, the F stars are whitish yellow, the G stars are kind of yellow, the K stars are orange, and the M stars are red. Now, if you look at any photo we take, you'll notice that you see a lot of stars. What you don't see is you don't see very many stars that are stars that you could readily identify color-wise until you get in close. And when you get in close, you'll notice that there's way more of these little tiny red ones than you ever realized. You see that? You see all the white ones, and you think, oh, mostly white stars. Yeah, not so fast, Kimosabi. Because if you look, you'll see all these red stars all interspersed throughout them. And that is the most prevalent star in the universe you're seeing right there. It is the M-class star, the M stars. These are the stars where they make up the most stars in any galaxy everywhere in the universe. They are the most popular star in the universe. And thus, they have the most planets around them of any planets in the universe. Of any stars in the universe. They'll have most planets around them. Just by sheer numbers.
If you see the Hertzsprung-Russell diagram, color on the left and color at the bottom, luminosity on the left. The sun is set dead in the center of the diagram.
Yeah.
It's under brightness or luminosity. Well, it's at 1. It's a logarithmic scale too. So 1 solar brightness right in the middle, going up and down on the left side, and 1 solar mass and 1 sun color, I guess you'd say, right in the center on the scale from left to right.
Well, it's a sun-based diagram. You know, it was based on comparing our sun to all the others. So when Henry Norris Russell and Ejnar Hertzsprung came up with that diagram, they noticed the strange characteristics of it. They noticed that there was a line going right down diagonally from upper left to lower right, where most of the stars appeared. That line they called the main sequence. Those turned out to be the stars that were just doing normal hydrogen fusion, hydrogen into helium, like the sun, normal stars. The stars that became supergiants, on the other hand, and giants and subgiants and bright giants, those stars weren't on that main sequence. They were actually doing something different. They were fusing other elements in their cores. At first, you could see how that could be pretty darn confusing. But it's actually pretty clear and makes a lot of sense once you look at the progression of fusion products in a star. Now, when the star comes off the main sequence, a heavy star, it goes up something called the AGB, the asymptotic giant branch. As it goes up there, it's turning into a red giant, and it's fusing other elements in its core, and in shells around the core, as a matter of fact. And that's what powers the star at that point. Eventually, it runs out of all of that. And when a star is on the AGB, the asymptotic giant branch, and it moves up there, when it becomes a supergiant, there's no happy ending for that supergiant. Okay? That supergiant is going to be obliterated in a supernova. Yeah. And stars like Betelgeuse used to be O-type stars. They used to be bright, hot blue stars, okay? And then it turned into a red giant. Betelgeuse is a very short time away, cosmologically, from its end state as a supernova. Gosh, I want that to be true. I had a dream last night that this year Betelgeuse was going to go supernova, Daryl. Yep, I did.
Well, we'll see.
I know, right? What can you say?
You know, well, I have mixed feelings about it. You know that. I mean, I'd hate to see Betelgeuse go away.
Oh, but think about what it will replace it.
Eventually, yeah. I'd wonder. I mean, if it took 1,000 years for the Crab Nebula to become what it is, will it take 1,000 years for Betelgeuse to become what it's going to be? I mean, we would just see the process that way, but you know, I'm sure it's going to leave. It's going to make quite an impression when it goes.
You betcha. You bet your sweet bippy. Rona Martin's laughing. Yeah, and so that's pretty cool. You know, and let's be clear. The belt stars of Orion. Alnitak's an O star, right? The leftmost star. That's going to go in a supernova. Rigel's going to go in a supernova. I mean, the face of Orion is going to change over the next few million years because all of those stars, they only live a few million years. So, and I've said this before, when Lucy, Australopithecus afarensis, was trudging around Africa in Olduvai Gorge, if Lucy had looked up at Orion 4.2 million years ago, she wouldn't have seen the Orion we see today. There would have been 2 stars in the belt, and Betelgeuse would have been a hot blue giant. You know, a hot blue star in the upper left. There'd be no color to it. You know, it's only since then that it's migrated up to the red giant path, and only since then that that the belt stars filled out with a full 3 instead of just 2. So the universe changes, but not at the scale of human lifetimes.
If you see a nighttime, if you see a long exposure photograph of the constellation or of Orion, you'll see evidence of lots of supernovas happening there in the past.
Like Barnard's Loop.
Barnard's Loop is a classic example.
Yeah. We'll talk about that. We might even see Barnard's Loop. We're here now. I think Orion is... Oh, I wonder.
Well, the whole winter circle is up by 11 o'clock or so now, I think.
Yeah, you know what? I want to see.
Maybe a little low to see from your roof of the observatory, but...
I know I'm pushing it, aren't I? Well,
take a look. Give it a go.
Well, it's 45 degrees. We might be able to catch the Horsehead Nebula. I don't know if we'll catch the Orion Nebula. But we can try it. We've been going for a while. It's after 1 a.m. here. Let's try it. Okay. We just did 28 here. I think that's more than enough, don't you think?
Sure.
And this is Northern Trifid, so we'll save it. There we go. Green bar. Save exactly as seen. Save exactly as seen, too. Okay. Now we'll clear. Come back
Uber
here.
Coup. There is a great channel on YouTube called Kurzgesagt, Kurzgesagt, I think. They do science article shows, and they're in sort of a cute cartoon format. They just released one recently about supernovas and how far away they might be versus how close they might be, and what effects they would have on our planet. So really informative. Betelgeuse is far enough away. About 700 light years, Mark?
750 or so,
It wouldn't really have any effect on us. Although, as we have both mentioned recently, when that gamma ray burst went off a few weeks ago, 2 billion light years away, and it had noticeable effects here on planet Earth. So that makes me kind of second guess that.
It changed ground currents.
It changed ground currents, and it had an effect on the extreme upper atmosphere, too. Yeah. From 2 billion light years away.
Oh, yeah. Okay, obviously we're facing the building, but just to give you a taste of what we're going to see once... first of all, this is Alnatak right here. You can see in the halo, you can see the edge of the building cutting in here. All right. But we'll just do just a 25-second shot just to give you a taste of what we'll see. All right. And you're going to see the red building again, but, I just want you to see what's coming up. It's coming to you. And...
Oh, no.
3, 2, 1, 0. Display. Yeah, it's a little messy because of obviously the roof, but you can see that's what's coming. If we color correct, it's going to be wrong.
Oh, probably just a few more weeks. It should be prime time.
I think so.
Oh, well, Orion.
Yeah, there's the horse head.
Yep.
There's Sigma Orionis. There's the Flame Nebula, and this is Alnatak. This star will be a supernova in, well, less than 2 million years anyway. Probably even less than that. Okay, unfortunately, it's just below the building for a little while longer. And I can't go to the Orion Nebula because that's even more below. However, let's see where Betelgeuse is in this. First of all, we'll come back. We'll be doing more with this later.
Michael, I wouldn't know where to start.
Well, what's he asking?
Where would I travel in space if I could instantly, or would you like some journey time for the experience? Journey time is going to be a really long time unless I'm going darn close to the speed of light. If I go at the speed of light, there'll be no time passage at all.
Oh, you didn't hear my talk before? Just generate some Kaluza-Klein particles and go into the bulk. Then you can punch in and punch out almost anywhere you want.
Highly speculative. There's so many places I'd like to see. Maybe one day when I shuffle off this mortal coil, I get to go see them all. The Whirlpool, Andromeda, M33.
Oh, you might be disappointed with the Whirlpool.
All the showcase objects. So. I'm sure by the time I'm no longer earthbound that I won't need a hot suit or anything, or I'd go check out all the neat stuff. We look at Betelgeuse.
Yeah, this is Betelgeuse right here. Yeah. Just checking out Betelgeuse. And everybody in the chat is thinking what I'm thinking. What if it went supernova right now while we watched it? What would we see? Well, what we'd see is we can simulate it actually. It would do, let's see. We'd see it looking like this. It would suddenly get really bright. We'll say, what's going on? You know? And then we'll be, man, it's what's going on with it? It's getting brighter. And then it's getting even brighter. And the next thing you know, it would be so bright. Look at, we got wind. Look at that. It'd be so bright that we would not be able to use our camera to capture it in a reasonable way. Which I think is exactly what we'd expect. Now, even if we go down to nothing here, Betelgeuse is still there. All right, and still bright. We're trapped. We got a little bit of the edge of the building in there. Now, Fantasy says, why can't we see the Orion Nebula? I mean, I'm seeing it right here. Yeah, but you gotta remember, we have a remote observatory, and it has walls and a roof. And so we have to wait for it to rise above the eastern side. We don't look in the east, typically. We look, in the south and the west because, from the east, that's stuff coming. So we can wait for it to come. We're just trying to push the limits right now. What does Izabela say? Mark, how would it be possible to communicate with ships in the bulk? Would radio waves work? Probably not. It's probably going to be a very different communication mode there. Hey, Curtis. Curtis Horn's here.
Semaphores, I bet.
Well, if you could see them. Yeah. All right, well, you know what, guys? Betelgeuse will be our last object. As you can see, there was some wind kicking up here, and every now and then you see that the image goes wonky. We won't be able to capture anything in a good manner right now, but it's okay. We went for a long while. We got a lot of stuff, and I'm glad you guys could come with us and hang out with us. I enjoy your company. Daryl likes your company on occasion. Most times he just says, I don't want them to come in, and I say, no, but they got to, and he'll give in.
I do not.
It's called a joke, Daryl.
Yeah, I know. Pretty small joke.
Ooh, yeah. We had fun, though. We had fun. So, guys, we'll be back. We're averaging every other day. And we'll come back and do this again real soon. And Michael, thank you for changing your name so that people don't just call you Hedrick because they don't know that's not your first name. That could be a first name. I know you as Michael. Anyway, you guys have a good time. Good seeing you all, especially to those who came in late. Curtis, good to see you, man. Hope things are going well. And we will talk again soon. So you have a good evening. And good night, all.
Good night, everybody.